For centuries, the fight for command of the seas has determined the rise and fall of empires and nations. To rule the waves, navies around the world have been locked in a battle to develop the most powerful and technologically superior vessels. In this episode, we chart a course from the once revolutionary steam-powered dreadnought battleships to the nuclear-powered fortresses that are the Nimitz-class aircraft carriers, and from the ever-evolving arms race below the surface to the new wave of amphibious craft and autonomous vessels above. This is the story of sea power. On the high seas, this is the height of technology. A guided missile destroyer, the USS Zumwalt is the most advanced ship from the world's most advanced navy. Fast, stealthy, and heavily armed, this vessel has been designed to combat the military threats of today and those of the future. With its futuristic appearance, the Zumwalt may stand out on the water, but its trapezoidal shape actually serves to hide it.
It's designed the way it is to reduce its radar cross-section, so if there's someone looking for it, if they can't see it with their eyes, then what they'll see on the radar is a much smaller return. They'll think it's something closer to a fishing vessel.
A big part of that comes from the ship's unusual hull, which narrows from the waterline to the upper deck. Known as a tumble-home hull, this design not only serves in stealth, it changes the way the ship moves through the water, slicing through waves rather than riding over them.
From a stealth perspective, you probably want a lot of sort of fairly straight angle panels that are not pointing straight back at any particular area.
Highly automated, the ship can run with as few as 130 crew members, less than half needed on similar-sized warships. The most powerful destroyer in the history of the US Navy, the Zumwalt is also the first naval surface combatant to run on all-electric propulsion. Driving its electric generators are a set of two of the most powerful marine gas turbines in the world, the Rolls-Royce MT-30, producing 78 megawatts of energy, enough to power 10,000 homes. The Zumwalt has more than it needs to drive its propellers and power the ship's service and combat systems. The excess energy is anticipated to power weapons and sensor systems upgrades, ensuring the ship remains at the cutting edge well into the future. For all its advances, the Zumwalt is not without its critics. The incorporation of a radical design with a host of experimental technologies has sparked concern as to whether this ship of the future can live up to expectations today. With only one completed and in service, the Zumwalt has yet to be tested in battle, and only time will tell if it charts a course for the future of the Navy. Since mankind could take to the sea, we have sought to control it. And naval warfare can trace its origins to ancient Greece, the Romans, and the seafaring raids of the Vikings. From ancient times, it was sail power that ruled the waves. But in the late 18th century, a new technology arose, bringing an end to the age of sail: the steam engine. First appearing on boats in the 1770s, steam engines used external combustion to harness the heat energy of steam, converting it to mechanical motion through a paddle wheel or propeller. Redefining what ships were capable of, the steam age gave rise to a new generation of vessel. No longer dependent on the vagaries of the wind, ships became faster and more reliable. As ships grew in scale and power, the first armoured vessels, the ironclads, emerged in the mid-19th century. Slow and cumbersome, it would take another boost in power before armoured warships would rule the waves. In 1884, British engineer Charles Parsons invented what he believed would unleash the full power of the steam engine, the steam turbine. Seeing the potential for maritime industries, he set about building an experimental ship that would demonstrate this increased power to the world. The first steam turbine-powered ship, the Turbinia, though not equipped to fight, would shape the future of warships. With Parsons' turbine generating 1,000 horsepower, he calculated a top speed in the region of 30 knots, a record-breaking feat for the day. The problem was that in testing, the Turbinia failed to perform, unable to reach even 20 knots. What followed was a 2-year period of intensive research that led to a breakthrough in the understanding of cavitation. Because water at a lower pressure boils at a lower temperature, the low pressure zone created by a spinning propeller can effectively boil seawater. The bubbles formed by cavitation are not filled with air, but with steam. As the steam bubbles implode, the resulting shock waves wreak havoc on any nearby moving parts, rapidly enhancing wear and dramatically decreasing performance. Parsons' research led him to understand that by increasing the blade size of the Turbinia's propellers, he could delay the inception of cavitation. Sporting this enhanced propeller system, the Turbinia took to the water again in 1897, reaching a top speed of 32.7 knots. It astonished onlookers and easily became the fastest ship of its day. The unprecedented power unleashed by the steam turbine engine was quickly seized upon by naval forces around the world, helping usher in a new era in battleship design, the dreadnought era. From the early 20th century, several navies around the world were toying with the concept of a battleship that would carry a uniform armament of heavy guns. Launched in 1906, it was the HMS Dreadnought that proved the revolutionary power of the concept. The fastest battleship at the time of her launch, the HMS Dreadnought was the first lead ship to be powered by steam turbines and sparked an arms race for bigger and better battleships that reverberated around the world. Fast and powerful, dreadnought battleships were characterized by the exclusive use of turbine propulsion for speed and an array of large caliber guns for fighting. At the time, naval guns were unguided, and gunners relied on the splashes of missed shots to adjust their aim. The development of rapid reloading 12-inch naval guns meant that gunners could zero in on enemy targets more quickly and with the weapon that actually mattered. Equipped exclusively with these weapons, dreadnought battleships became the most lethal force on the water and the dominant naval power throughout the First World War. Technical developments continued to advance rapidly, and by the dawn of the Second World War, the dreadnought class was superseded by a new style of multi-role battleship. The Iowa class represents the culmination of the battleship era and the ultimate decline of such ships in the ever-evolving world of naval warfare. The first of the 4 Iowa-class ships entered service in the US Navy in 1943, representing the most powerful class of battleship ever built.
With her complement of about 2,000 men, the giant fighting ship goes through the battle maneuvers in readiness for that moment when her full weight will make itself felt in battle itself.
speed, once a guiding principle in the dreadnought era, had been sacrificed in preceding classes of US battleship in favour of heavier armour. But with the longer-hulled Iowa class, speed was back at the forefront. And courtesy of 4 cross-compound steam turbine engines, they were the fastest battleships in the world, capable of a top speed of 32.5 knots. With battleships having long since moved away from the dreadnought all-big gun configuration, the Iowas carried a range of firepower, from its array of small 20mm anti-aircraft cannons to its 9 huge anti-ship and shore bombardment guns. Lobbing 16-inch shells for an incredible 32 kilometres at maximum range, the devastating projectiles could spend nearly a minute and a half in flight. For all their firepower and speed, in the Second World War, decisive naval battles were becoming a thing of the past, and the Iowas were relegated to an artillery support role in the island-hopping campaigns of the Pacific Theatre. All the while, debate continued as to the relevance of battleships. In a time when superior power was to be found above the ocean and below it. And it was below where the greatest revolution in naval warfare took place. With the widest range of types and capabilities of just about any aquatic vessel, submarines changed the dynamics of naval power forever. Experimentation with submersible craft dates back to the 16th century. But the myriad of engineering challenges posed by the underwater environment, from stability and navigation to life support and pressurization, meant that it was hundreds of years before viable designs were proven. And for this, much of the credit goes to one man. Considered the father of the modern submarine, John Holland was an Irish-born engineer who, in the late 19th century, built the vessel that proved the possibilities of underwater craft.
John Holland was an Irish-American who developed basically the modern concept of the submarine by understanding the buoyancy and the weight relationship and understanding how to make the submarine dive and return again safely to the surface in a consistent manner.
Combining an internal combustion engine for travel on the surface with an electric motor for propulsion beneath, Holland's prototype was the first vessel to run for any considerable distance while submerged.
It was that enabling technology of the propulsion that enabled both flight and also it enabled submarines.
The US Navy purchased Holland's model in 1900 and quickly ordered 6 more, inaugurating the first submarine fleet in the world. Today, what we know as the submarine owes much to the military, and the military was drawn to submarines for one reason: their ability to be weaponized. Named after the torpedo fish that hunts by delivering a stunning shock to its prey, the torpedo remains the most lethal anti-ship and anti-submarine weapon ever invented. While work on underwater missiles had taken place previously, it was English engineer Robert Whitehead that is credited with creating the first self-propelled torpedo in the mid-19th century. Fired from a tube above or below the water, Whitehead's torpedo used a 3-cylinder compressed air engine to travel towards its target. With its worn nose designed to detonate a charge of explosive gun cotton on impact, Whitehead's chief innovation was the addition of a hydrostatic valve and pendulum balance connected to the rudder, allowing the weapon to maintain a constant depth. The latter addition of a gyroscope mechanism allowed the torpedo to correct its course against underwater currents, greatly enhancing its accuracy. Devastating to ships and difficult to defend against, the torpedo was the ultimate naval weapon. And able to close into an effective range while undetected beneath the surface, submarines were the ultimate craft to deploy it. Thus, it was the torpedo that transformed the submarine from experimental oddity to fearsome weapon of war. And throughout the 20th century, there were perhaps no submarines more fearsome than the U-boat. German for undersea boat, these craft, like all submarines of the era, were more submersible ships than true submarines.
And the U-boats in the First World War and the Second World War were just continuations of the same technology and the same design and the same thoughts that Holland had.
Sinking beneath the surface to avoid airborne attacks and to conduct stealthy torpedo strikes on enemy craft. It was this underwater ability that made the U-boat so deadly throughout both world wars. The most significant of the U-boats was the Type 7, relatively cheap and quick to build. During the Second World War, the Type 7 formed the backbone of the German U-boat fleet, with over 700 produced. And it was this vessel that rose to prominence in the longest, largest, and most complex battle in naval history.
At the beginning of the Second World War, submarines were being deployed by the Germans to sink the merchant ships that were going from America to support the UK. And in fact, Churchill is quoted as saying the most dangerous thing for him during the Second World War was the Battle of the Atlantic.
The German U-boats, led by the Class 7, patrolled the Atlantic in dreaded wolf packs. With their small profile and tight living quarters for their small crew, the Type 7s were all about agility and armament. Running primarily on the surface under diesel engines, the Type 7 was capable of rapid crash dives, and this favoured manoeuvre saw them disappear beneath the waves in as little as 20 seconds. Here, their combustion engines could not be supplied with sufficient oxygen, and they switched to their less efficient electric motors. What was sacrificed in efficiency was gained in stealth, and listening from the depths with advanced underwater microphones, they set their torpedoes to sink dozens of warships and millions of tons worth of merchant cargo. But the tide eventually turned against the U-boats, and the hunter became the hunted. The breaking of Germany's Enigma code, along with new Allied tactics and weaponry that capitalized on the U-boats' limited underwater performance, rendered them little more than sitting ducks. In the closing stages of the Battle of the Atlantic, these craft came to be referred to as iron coffins. Developed in the years between the First and Second World Wars, the T-class submarine was the British Navy's attempt to command this new aquatic battlefield. Along with an enhanced hydrodynamic structure, the T-class subs carried twin 1,450 horsepower electric motors to provide a greater capacity for underwater performance. Nonetheless, along with other subs of the day, the T-class remained faster and more efficient on the surface. And here, the T-class ran on twin 2,500 horsepower diesel engines, with an increased fuel capacity to afford a wider range and longer mission durations. But the T-class submarine's real advantage was simple. It could fire more torpedoes. With 4 external torpedo tubes and 6 tubes built into the bow, it was the first submarine to ever carry such firepower. The design proved a success. Playing a major role for the Royal Navy in World War II, the T-class was upgraded during the Cold War to target Soviet subs, remaining in service until the 1970s. With submarines revolutionizing naval warfare from below, surface vessels needed to adapt to neutralize the threat. Employed by both sides during the First and Second World Wars, merchant ships carrying concealed weaponry were an early attempt to do just that. Known as Q ships, they were designed to appear as easy targets, luring submarines to the surface where they could attack via deck guns rather than firing their limited torpedoes. Even if struck by torpedo attack, Q-ships carried a cargo of light wood in order to remain afloat, encouraging the sub to expose itself in order to finish off the apparently foundering vessel. When the submarine surfaced, the Q-ship's panels dropped to reveal its own deck guns. Using the elements of surprise to overwhelm its otherwise superior adversary. But the submarine menace would never be neutralized without more sophisticated methods. And one naval vessel proved especially adaptable to the role: the frigate.
Today, post-war, the frigate is generally used to define a surface ship which has as its specialization hunting submarines.
Warships built for speed and maneuverability, frigates were increasingly retrofitted with anti-submarine technologies during World War II. And this capability would be built into new models in the latter half of the 20th century. Models like the Leander class. First commissioned by the British Royal Navy in 1963, the Leander class became one of the most numerous and long-lived frigates in modern history, with derivatives of the design being adopted by other navies around the world.
The first thing the frigate has to do is be very quiet. So one of the key things about the frigate is to make sure that the speed at which cavitation occurs is as high as possible, so that when it's hunting for a submarine, it's not making any cavitations.
Being quiet is one thing, but anti-sub vessels also need to be good listeners. To that end, they were equipped with an enhanced detection system in the form of VDS, variable depth sonar. Towed behind the ship, the Leander's VDS array emitted sound waves to echolocate objects underwater, determining bearing, range, and depth. With their position revealed, enemy submarines could be fired upon using an anti-submarine mortar system known as Limbo. Launching depth charges in any direction around the ship, Limbo used 3 barrels to drop the explosives in a triangular pattern around the target, maximizing the chances of a hit.
The other thing an anti-submarine frigate will have is a helicopter. The helicopter will be designed for anti-submarine purposes, and it will be able to fly and put a dipping sonar in the water and listen for submarines.
Due in large part to these enhanced capabilities, not a single ship among the 26 Leanders was ever sunk by enemy action. But the next leap in power would not only revolutionize submarine warfare, it would redefine naval forces the world over. The nuclear revolution of the mid-20th century boosted both the power generation and the armament of naval vessels like nothing before. Thanks to nuclear power, submarines became true submersibles. Capable of remaining beneath the surface indefinitely, subs were now limited only by the supplies they could carry and the endurance of their crew, giving rise to a new generation of vessel.
Mrs. Eisenhower took 2 hands to the job when she named and launched the American submarine Nautilus at Groton, Connecticut. The vessel is the world's first atomic-powered submarine. It's said to have cost over £10 million to build.
Launched in 1954, the USS Nautilus represented an unparalleled breakthrough for submarines. Taking its name from the vessel in the science fiction classic 20,000 Leagues Under the Sea, this deep-diving giant turned imagination into reality.
The key thing about the Nautilus, that was the first submarine to operate under nuclear power. And until that had happened, nobody really knew whether they could run a nuclear power station in a submarine. I mean, it's quite crazy thought, really, to take a nuclear power station and put it into the tiny little confines of a submarine.
With diesel-electric submarines required to spend the majority of their time on the surface in order to charge their batteries for limited dives, non-nuclear subs were limited mainly to coastal defence. The Nautilus was designed to travel much further afield and primarily underwater. Among the many records for distance and speed that this new breed of submarine set, in 1958, the Nautilus travelled beneath the Arctic ice to become the first watercraft ever to reach the North Pole. Core to the incredible range and ability of the Nautilus was its S2W pressurized water reactor. As the atoms of nuclear material split, they generate heat. A pressurized water reactor uses a primary coolant system to circulate water through the reactor and absorb this heat. Pressurized so as not to boil, the now heated water in the system passes through a steam generator, where it transfers its heat to the secondary, unpressurized coolant system. With the water in the secondary loop vaporizing, steam is formed, which is directed to spin the turbine generator and produce the vessel's electricity.
The small nuclear part, which is shielded, of course, from the people, is used to heat water into steam. The steam is then used to drive a steam turbine. The steam turbine then drives the shaft. So basically that's how the process works.
Silent, consuming no air and producing no emissions, nuclear power was perfectly suited to submarines, and the pressurized water reactor became the basis for nearly all the US Navy's nuclear-powered subs, as well as its surface combat ships. The first of its kind, in operation, the Nautilus revealed a number of design and construction shortcomings.
Nowadays, submarine hull-shape design is quite different. It's not designed for running on the surface with the occasional trip underwater. It's designed underwater. And on the surface, it looks really odd because it's just making all the wrong waves.
Its record-setting feats notwithstanding, this vessel was equally influential in identifying areas that future subs needed to improve upon. The improvements in submarine technology led to a class of sub designed to combat an extremely challenging adversary, other submarines. Hunter-killer submarines, like the US Navy's fleet of 13 Virginia-class vessels, are designed specifically to attack and sink other craft, above the surface or below. And it's below, in conflict with other subs, where technical superiority is everything. The first thing is detection. Submarines sail blind, dependent on sonar and radar to navigate their way and identify targets. The Virginia class is equipped with an array of sensors to enhance its detection abilities, including thermal imagers, laser rangefinders, and low-light high-resolution cameras. Needing to remain ahead of the competition, upgrades are constantly installed.
Nowadays, submarines have tiles around the outside of the submarine to stop noise going out of the submarine.
Known as anechoic coating, these rubber tiles not only reduce the sound emitted from the submarine, they also absorb sonar pulses, decreasing the Virginia's return signal to any vessels listening in. After targeting an enemy and closing in undetected, the Virginia-class submarine can launch its attack. Fitted with 4 torpedo tubes and 12 missile tubes for its Tomahawk cruise missiles, once the command is given, the game is over for any vessel this hunter-killer has in its sights.
There would be very few places on this planet that could not be attacked by a nuclear submarine. Just even a nuclear conventional submarine, not a nuclear ballistic submarine. With the Tomahawk missiles, cruise missiles and so on, they can fire to just about anywhere on the planet.
And thanks to the 40,000 horsepower generated from its nuclear power plant, the Virginia and its 134 crew can clear the area quickly and quietly with a top speed of 25 knots. Known disarmingly as boomers, these vessels are the culmination of the underwater arms race. With the Cold War driving the proliferation of nuclear weapons, nuclear-powered submarines equipped to carry and launch ballistic nuclear missiles became the most powerful vessels in the world. It was Russia in the 1950s that claimed the dubious honour of becoming the first nation to equip a sub with nuclear warheads. The US was quick to follow suit, and these two superpowers have continued to dominate the deployment of nuclear ballistic submarines.
And the first of the ballistic missile submarines was the George Washington class. The George Washington was the first submarine to fire a ballistic missile from underwater.
Number 2 goes up, described by official observers as a little better than the first, and the first was excellent.
Featuring similar designs to hunter-killer subs, boomers were built larger to accommodate their nuclear missile payload. Beginning service in 1981, the 6 subs of the Russian Typhoon class remain the largest submarines ever built. They can comfortably accommodate their 160-member crews for submerged missions lasting months at a time.
The Typhoon was so big and strong, and it was designed to go under the ice, that one of the concepts of the Typhoon was that it would survive the first strike. The whole object of the deterrence in the Cold War is that nobody would strike because there's no such thing as a second strike.
Launched in the same year, the US Navy's Ohio class may have been smaller, but it came equipped with an overkill of 24 nuclear ballistic missiles, the largest armament ever carried by a submarine. Fired from the launch tube by gas pressure, boomers can project their missiles with sufficient velocity to reach the surface from 50 meters below. From there, rocket motors engage to carry the missiles, along with their multiple warheads, with pinpoint accuracy for thousands of kilometers. With the nuclear-powered submarine's range limited only by food supplies, these vessels can circumvent the oceans virtually without end and virtually unnoticed, posing an insurmountable threat to both sides.
Both the British and the Americans are actually actively, right at the moment, developing the next boomer class. It's still in the early design stage, and it would be highly classified.
To this day, boomers maintain an uneasy stalemate of mutually assured destruction. Just as the nuclear revolution changed what naval vessels were capable of, the rapid evolution of air power changed what naval vessels were for. With early 20th century fighter aircraft boasting greater range and precision than naval guns, a new kind of ship was needed to serve in a new kind of war. While the idea of a ship that could launch and recover aircraft is almost as old as flying itself, this is the vessel that first demonstrated the offensive power of aircraft carriers to the world, HMS Illustrious. Entering service in the British Royal Navy in the first year of the Second World War, HMS Illustrious carried a complement of approximately 1,300 men, along with 36 aircraft. Measuring 225 metres in length, she was not a big ship by modern aircraft carrier standards, and this was by design.
Originally it had capacity for just 14 aircraft, but had the Sea Dart long-range surface-to-air missile. Early in its career, the Sea Dart was removed to provide extra capacity, and then the ship could take about 22 aircraft.
In order that Illustrious protect its valuable payload of planes and aviation fuel against enemy attack, the below-deck hangar was heavily armoured. Placing a great deal of weight high in the ship, concerns over stability meant the hangar was limited to just a single level, essentially halving the ship's carrying capacity to ensure its survivability. Capable of travelling at 30 knots under full load, Illustrious was powered by 3 Parsons steam turbines. 3 drum boilers use a triangular layout to achieve a high rate of evaporation. With 2 water drums below and a furnace in the centre, the steam drum collects the saturated steam on top, Superheaters within the tube bank enhance efficiency by vaporizing the remaining water droplets in the wet steam, supplying dry, high-pressure steam to the ship's systems. Using heat to generate steam, boilers preceded nuclear reactors as naval power plants and remain in common usage on ships today. And this is the height of naval power today. The US Navy's Nimitz-class supercarriers.
The Nimitz-class carrier is an American class of nuclear aircraft carriers. At the end of World War II, aircraft carriers grew in size enormously, driven by two things. One of them was the jet aircraft. The other was the development of the atomic bomb.
In service since 1975, each of the 10 Nimitz-class carriers stands 20 stories above the water, stretching over 330 metres across it, capable of carrying 130 aircraft and crewed by a contingent of 6,000 personnel. Each vessel is simultaneously a ship, an Air Force base, and a small city. At the time of construction, the Nimitz class were the biggest warships ever built. Having served in nearly every crisis and conflict the United States has been involved in over the last 40+ years, these trusty ships are projected to provide the bulk of the Navy's carrier force for at least another 20 years. A big part of the Nimitz class's longevity is its nuclear power plant. With 2 Westinghouse 4AW pressurized water reactors, each ship generates 190 megawatts of electricity, enough to power 47,500 homes. Capable of operating for 20 years without refueling, these supercarriers use their reactors to drive 4 propeller shafts, achieving an official top speed of over 30 knots.
The advantage of nuclear power in these ships, it gives them in fact the ability to steam at high speed virtually limitlessly. But they have another advantage as well, and that is that if you have a nuclear power plant, you have a great deal more room in the ship for fuel for aircraft and munitions for aircraft.
Certainly people say that the most dangerous place on the planet is on the flight deck on an aircraft carrier, because there's aircraft taking off and landing and you're standing right next to them. Have you ever gone out onto an airport and stood where the aircraft are? You kept well away. But they have to be right next to it. They're manoeuvring the aircraft are turning, and then they're letting it go. And meanwhile, another aircraft is landing. If they step in the wrong place, they're going to get sucked up into the engines or run over by an aeroplane.
While the US government has neither confirmed nor denied the presence of nuclear weapons on its aircraft carriers, the Nimitz class are known to be equipped with missile defense cannons as well as anti-aircraft and anti-ship missile launchers. Along with the Kevlar armour coating vital spaces, the supercarrier's armament is the last line of defence, and the real protection is provided by the strike force it travels with. Costing around $4.5 billion each to construct. In conflict, this makes them a prized target for the enemy. As such, they never sail alone. Made up of at least 1 submarine for protection from below and several varying warships and supply vessels on the surface, the already intimidating supercarriers are escorted by an equally intimidating strike force to ensure the objectives of their deployment are met. Evolving from aircraft carriers, a new kind of naval transport vessel emerged. One that could extend the Navy's reach from the sea onto the land. The Amphibious assault ship. The first amphibious assault ships from the 1950s were converted from small aircraft carriers, and even modern purpose-built vessels bear a strong resemblance in their design. While amphibious assault ships have maintained the ability to transport fighter aircraft, their landing decks are typically used to carry attack and utility helicopters in order to land troops and supplies into hostile territory.
The Wasp-class landing helicopter dock. They're the largest amphibious ship in the world, and they have a combination of a flight deck, large helicopter hangar, a large vehicle deck for all the associated equipment that will be landed, a large troop capacity, and a well deck that can take up to 3 large landing craft.
Located at the waterline in the stern of the ship, the hangar-like well deck is essentially a floodable garage, housing everything from small boats to huge hovercrafts. Dropping its bow door, the well deck lowers to allow water to flow in, enabling landing craft to launch from and dock within the ship itself.
It's really designed for a large amphibious operation. It has quite elaborate command and control facilities on board the ship. And also the air-cushioned landing craft, the LCACs, allow the troops to go to the beach at quite high speeds, so up to about 40 knots or 70 kilometres an hour, and that reduces the risks that the troops and stores have during that vulnerable period.
The amphibious assault craft allows the transport of troops, supplies, even tanks from the sea to the shore without the help of a safe harbour. Coming in an array of shapes and sizes, the versatile amphibious assault ship has proven its place in navies around the world. And in military engineering, the quest for improvement is relentless. This experimental craft is part of that quest. Known as a surface effect ship, or SES for short, it combines elements of a hovercraft with a catamaran to achieve enhanced performance. This model, the SES-100B, was built for the US Navy in the 1970s to test the feasibility of the surface effect concept for combat situations. With buoyant twin hulls like a catamaran, the vessel has excellent stability. By employing a hovercraft air cushion, the SES-100B is able to rise up, leaving just a small portion of its hull submerged. Operating almost completely above the water, the SES has achieved speeds in excess of 96 knots. Unlike fan-driven hovercraft, the 100B runs on twin semi-submerged propellers, and the key to its remarkable pace is in the ability of these propellers to achieve supercavitation. With cavitation creating steam bubbles in water, supercavitation takes advantage of the phenomenon by creating bubbles large enough to encompass an object. In this case, the propellers. With the propellers travelling through pockets of air rather than water, skin friction drag is greatly reduced, translating to much higher speeds. But with its rigid hulls, the SES-100B lacked the land-going capabilities of its amphibious counterpart, and whilst having great influence on civilian vessels, never made it into military service. Bridging the gap from ship to shore is the ultimate in amphibious vehicles. Gliding over water and land alike, landing craft air cushions, known in civilian terms as hovercraft, are capable of penetrating over 80% of the world's coastlines. All while carrying up to 180 troops, or even a tank.
So the LCAC is one of the largest of the landing craft that are currently in use. And to give you an idea of its size, it's about 190 tons in weight, and is able to carry about 60 tons of either passengers or equipment.
Serving in the US and Japanese navies, these craft literally fly over mines or shallow obstacles that would disable traditional hulled landing craft. And with their tremendous over-beach performance, landing craft air cushions, LCACs for short, can land just about anywhere, making them incredibly difficult for enemy forces to defend against. Powered by 4 gas turbine engines, LCACs rest on a rubber skirt, which serves to trap a cushion of air under the craft. Holding it high above the waves and any obstructions on the land,
its main purpose is to take troops, soldiers, from an amphibious ship that is over the horizon and get to the shore as quickly as possible with the largest load of troops as possible.
With its 4 turbines providing close to 19,000 horsepower, LCACs can maintain speeds of over 40 knots for more than 320 kilometres. They can also carry payloads of up to 75 tonnes. While this carrying capacity and speed makes them ideal for rapid insertions of troops and hardware, the light touch of their air cushion also allows them to serve in mine countermeasure operations. But LCACs do have their drawbacks. Noise and spray levels are high, limiting the hovercraft's use in stealth missions. And akin to manoeuvring a puck on an air hockey table at highway speeds, handling is exceedingly difficult. With a turning radius of nearly 2 kilometres and requiring over 450 metres to stop. But this experimental craft could be the US Navy's ultimate solution in connecting sea to shore. The Ultra Heavy Lift Amphibious Connector, UHAC for short, is a half-scale prototype of the vessel that may replace the Navy's hovercraft fleet. Essentially a floating tank, the UHAC runs on 2 tracks comprised of dozens of dense air-impregnated foam blocks that provide buoyancy as they paddle through the water and traction as they roll across the land. While about half the speed of the current fleet of landing craft air cushions, the full-scale version of the UHAC is proposed to carry loads more than twice as heavy and travel twice as far. And with the ability to scale obstacles as high as 3 metres, the UHAC is set to extend the Navy's reach even further inland. Today, the large-scale naval technology is giving way to smaller and smarter systems of control over the seaways. This is the Sea Hunter, an experimental, unmanned vessel from the Defence Advanced Research Projects Agency. It is poised to patrol the open seas for the US Navy, guarding against intrusions from enemy subs. With its trimaran design, affording excellent seaworthiness even in the roughest conditions, the Sea Hunter will brave the oceans alone, maintaining a constant vigil.
So the trimaran shape definitely has advantages in seakeeping. You can have a very, very slender central hull and the outer hulls set back, so it can have advantages with the seakeeping performance of those vessels. By making the hulls extremely narrow, then you can reduce the amount of power required to propel those vessels going forwards.
Running on diesel propulsion, the craft's top speed of 27 knots allows it to keep pace with sprinting subs, and its transoceanic range of 19,000 kilometres means it can follow its quarry for up to 90 days non-stop. Highly autonomous, the unmanned Sea Hunter can patrol without human input, using optical guidance and radar to reliably avoid obstacles and other craft. Operationally, it will be observed and controlled when necessary by a remotely stationed human. Unarmed, the Sea Hunter's power is in its ability to detect even the best hidden vessels. Mid-frequency sonar will locate long-range targets, with high-frequency sonar refining tracking once the Hunter closes in. Built from lightweight radar translucent carbon composite materials, the Sea Hunter will be near invisible to the submarines it stalks. Ruling the waves with intelligent automated technology, the Sea Hunter is a vision of the future Navy, a future that is already upon us. From the age of sail to the age of steam, from battleships to aircraft carriers, and nuclear subs to alternative and autonomous craft, naval vessels have kept pace with the great technological shifts in history. And today, as ever, the naval forces remain at the ready, anticipating the next leap in seagoing power. The sea is where life on Earth began. And for man, himself a product of the sea, the journey to explore and better understand this primordial world is in many ways a journey of self-discovery. With waterborne craft the oldest vehicles known to history, the sea has driven invention since ancient times and continues to drive it today. In this episode, we set sail from the hydrofoiling catamarans that forever changed the America's Cup to the often fatal quest to set motorised water speed records, and from the unstoppable power of nuclear icebreakers to the unseen potential of interstellar solar sails. This is the story of sea power. Over 70% of the planet we call Earth is covered by water. And more than 96% of that water is contained in the sea. Beautiful and ferocious. The sea is a world unto itself. A world of legends and awe-inspiring power. Power that we have sought to harness. And power that we have done our best to withstand. Yet for the remarkable advances that have carried us further and deeper, we have barely scratched the surface of this mysterious world. And 95% of it remains unseen by man. This experimental craft is seeking to create a completely new mode of waterborne travel. Mimicking the anatomy of water-skimming insects, this Wave Adaptive Modular Vessel, or WAM-V for short, has already earned the nickname Spiderboat. Designed by Italian engineer Ugo Conti, this scaled-down model is testing the radical technology for smoother, more efficient motion on the water, with the ultimate craft set to be a total of 29 metres long. With titanium shock absorbers mounting the 4 legs that connect the superstructure to the catamaran outriggers, the WAM-V is able to travel with the movement of waves rather than through them. Skimming over the water for incredible fuel efficiency, the full-scale Spiderboat will carry more than 7,500 litres of fuel in its outriggers. And set to be powered by twin Cummins Marine Diesel Quantum Series engines, the final craft will be capable of crossing the Atlantic Ocean with an impressive top speed of 30 knots. With inflatable hulls, the Spiderboat can be beached without damage. Its unique properties allow the craft to fold down for easy hauling out of the water. Designed to carry a range of modular cabins, the Spiderboat is built to allow a range of interchangeable uses, theoretically switching from research operations to rescue work quickly and easily. Fast, efficient and versatile, the WAM-V has already attracted interest from the US Navy. While experimental today, Spiderboat technology may be commonplace on the waters of tomorrow. Rising up above the water to cut down on surface drag and boost speed, these are boats that fly.
It's an amazing thing to watch, and it's an amazing thing to be involved with some of the engineering and what's called the Moth International Sailing Class dinghy. They've been hydrofoiling since the early 2000s.
And it is these small single-sail, single-person yachts that did more than any other to demonstrate the technology, hailed among the most revolutionary developments in marine engineering. The hydrofoil. Like the aerofoil design of an aeroplane's wings, hydrofoils serve to generate upwards lift.
The first thing you notice once you come up on the foils is everything goes quiet. it goes complete. I mean, you don't get this slap, 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 slap on the water. It just goes quiet. And it's like, what happened?
As the craft gains speed, the angled shape of the foil creates different pressure systems in the water, essentially accelerating fluid downward to drive the hydrofoil, and the boat up. With the bulk of the craft now travelling through the air, an environment approximately 1,000 times less dense than water, the resistant force of drag is drastically cut down, translating to an increase in efficiency and therefore speed.
It's just lifted out of the water and the drag reduces by probably a factor of 5 and accelerates. And once it accelerates, you're actually moving through the wind faster as well. So you're actually harnessing more of the wind, because as you move through the wind faster, you can actually grab more power out of the wind.
First tested on motorised boats in the late 19th century, while hydrofoils proved successful in enhancing efficiency, the complexity and cost they added to construction prevented a wider adoption of the technology in large motorcraft. Small-scale racing yachts had more freedom and incentive to experiment, and it is in the moth class that hydrofoils have really made their mark. Upscaling the hydrofoil technology developed by the smaller moth class, the new generation of racing catamarans have made the next leap in power. Capable of travelling at more than twice the speed of the wind, these boats turbocharge the most hotly contested race in sailing, the America's Cup.
So in 2013, the America's Cup reinvented itself and made 72-foot catamarans weighing about 6 tonnes each.
Thanks to their wide multi-hull design, catamarans can accommodate a greatly expanded sail area while maintaining a lightweight, stable platform, making them the ideal vessel for hydrofoiling. Nonetheless, each of the carbon fibre hydrofoils must be able to withstand pressures of around 15 tonnes, more than twice the weight of the vessel, while maintaining a thin profile about the size of a surfboard.
We can now construct composite components on very high stiffness and very high strength and very, very low weight, which is exactly what we need to make these hydrofoil boats fly.
And it's in flight that these remarkable craft are achieving unprecedented speeds for sailing vessels.
And eventually the entire hull is out of the water, so we've got these large 6-ton vessels being completely supported by hydrodynamics. That allowed those vessels to go from, say, 30 knots up to almost 50 knots very, very quickly.
Beyond the benefits of speed, the durability of the vessel may also receive a boost. Rather than slamming and crashing their way over the waves, hydrofoils travelling above the water are placed under less structural stress than traditional craft. These gains are not without losses, and there are concerns as to whether the power of these vessels is simply too much for a sailboat to possess. However, with the transformation of the America's Cup into something closer to F1 racing on water, the pursuit of speed shows no sign of slowing down. Combining speed with comfort, these commuter ferries are the Concords of the water. Australian manufacturer Incat has revolutionised the catamaran design to achieve the remarkable distinction of building some of the fastest ships in the world.
Well, a catamaran's a very old form of marine transport, of course. It's been around for thousands of years, one way or the other. Typically, catamarans are long and skinny hulls, which on their own would not be very useful, but when you put two hulls together, you get a nice big wide platform, which is very good for carrying light cargo, people, motor cars, etc.
Catamarans are ballast-free and therefore lighter, with lower hydrodynamic resistance than usual monohull ships. Because of this, they require less propulsive power from their motors, resulting in a very fast ship.
The boats today are replacing monohulls left, right and centre because they're more economical, they are lighter, they are wider, bigger, etc.
Incat has built a reputation on manufacturing these super-fast ships. In fact, Incat has built the last 3 consecutive winners of the Blue Riband, the prestigious award for the fastest crossing of the Atlantic by a commercial passenger ship. To date, they have built over 90 catamarans. The extraordinary speed of their vessels is attributed to 2 factors: state-of-the-art design and exceptional power. Their catamarans' long, thin hulls have a reduced buoyancy so as to pierce through waves rather than ride over them, providing a smoother, more comfortable ride for their passengers, as well as reducing mechanical stress on the vessel. Incat's fastest catamarans are powered by gas turbine jet engines, modified to breathe water rather than air. With water entering the jet units through intakes on the bottom of the boat, the engines accelerate and fire the water backward at high velocity, forcing the vessel forward in the same way a jet propels a plane.
A lot of the power of a normal propeller is lost off the tips. It goes sideways off the tips of the propeller. If it's in a tunnel, that power is more contained. So water jets are more complex, but generally at high speed more efficient.
With advanced acceleration over propellers, water jet propulsion affords high efficiency at high speeds and excellent manoeuvrability for docking at low speed, perfect for a quick commute and an easy disembarkation. When it comes to moving non-human cargo, the economy of scale has driven the development of true giants of the sea. And with big ships comes big engineering challenges and even bigger power. Giant container ships, or box ships as they are affectionately known, are the unsung heroes of mechanical engineering. And among these waterborne leviathans, it is the Maersk Triple E class that are the most advanced in the world. "400 metres long and 59 metres wide. The Triple E class is only a few metres larger than a standard box ship. But thanks to a clever layout, they can carry an additional 2,500 containers. In transporting their enhanced load, it is the slow and steady technique of the Triple E class that wins the race.
The vessel needs to actually float in a different position and orientation in the water, so that its hydrostatic forces are changed remarkably from when it has nothing on board to when it has everything on board, and the engineering actually needs to adapt to that. When a large bulk carrier is being filled, there's a very definite and very specific way that the weight needs to come on board. If it comes on board in an incorrect way, the ship can literally break in two, because the structure is not designed to carry that load in a particular condition.
While most container ships cruise at around 25 knots, the Triple E class are designed to use a technique known as slow steaming, running at an optimal speed of around 19 knots. Reducing fuel consumption by close to 60%, the slow steaming Triple E class can transport more containers with less power. But on this scale, going slower is not just a matter of easing off the throttle. The first challenge is finding engines that can run with slower revolutions. The Triple E class settled on twin two-stroke diesel engines, each with an ultra-long stroke. Fitted with a waste heat recovery system, the engines use their own exhaust gases to comfortably produce a total of 86,000 horsepower. But having efficiency in an engine is one thing, retaining it in a propeller is another. Propeller size is limited by the draft of the ship, the distance from the water surface to the lowest part of the hull. With the Triple E class requiring a propeller with a diameter larger than its draft, they opted for what's known as a twin skeg system, using two smaller propellers to achieve the combined diameter needed for maximum pushing power. And while a standard large propeller has 6 blades, two smaller propellers can each have 4. Less blades means less resistance, and less resistance means even better efficiency. At sea, big ships have plenty of room to operate. But when docking or departing from the confines of a port, they often require some gentle persuasion. Built to push around vessels more than 1,000 times their size, tugboats have an extreme power-to-weight ratio. Compact craft with disproportionately large engines, they are the muscle cars of the marine world. And without them, megaships would never be able to dock. With their oversized engines producing upwards of 27,000 horsepower, tugboats pack a lot of punch.
The size of the engine compared to the size of ship is huge. So they can basically push or pull. They can either push with a rubber fender or they can put a rope to the ship and pull the ship.
And with a narrow margin of error between a successful docking and a hugely expensive crash, most tugboat engines feature 2 of each critical part to guard against failure. But being powerful and fail-safe isn't enough to pull and push 100,000-ton ships through narrow waterways. Tugboats need to be agile, making them half sumo wrestler, half ballerina. Most modern tugboats derive their agility from azimuth thrusters, propeller units capable of rotating a full 360 degrees. With the propeller directing thrust, the need for a rudder is eliminated. The addition of ducted shrouds, known as court nozzles, around the propellers provides enhanced efficiency. Directing the water entering and exiting the propellers into a linear configuration, the tugboat's thrust-to-power ratio is given a helpful boost at low speeds, right when they need it most. With most tugs confined to sheltered waterways, seafaring is not a priority, and their hulls have evolved a heavy displacement design to suit their purpose. Already low-riding vessels, when a tugboat powers up, its hull sinks even further into the trough of its own wake. In the exact opposite of a hydrofoil, this sinking effect provides more contact with the water. More contact means more friction, and when shoving oversized ships around, the more resistance a tugboat has against the water, the better.
It's difficult to predict the trajectory of a ship, given not just the control forces involved from the propeller and the rudder, but also from environmental effects such as wind or current. And so all those effects come into play. So the tugboats are used to mitigate any problems. For example, if a ship were to run aground, then it would be a major catastrophe in a port because the port wouldn't be able to operate.
A triumph of power and design. As megaships continue to grow, the dependable tugboat will be there to shoulder the burden. While the transport of cargo has given rise to megaships, so too has the transport of people. For hundreds of years prior to the development of long-range aircraft, ocean liners were the dominant mode of travel between continents, driving the development of seafaring giants. With the travel industry powering the construction of ships, each bigger and more excessive than the last, this growth has not been without disaster. Once the biggest moving vessel ever made by man, today, the RMS Titanic looms large from its grave beneath the waves as the most infamous ship in history. This is all that's left of the vessel that was once celebrated as being unsinkable.
Titanic was built by Howland and Wolff in Belfast in Northern Ireland. She was about 47,000 tonnes, not particularly a big ship. The present famous liner Queen Mary II, the Cunard line for example, is 3 times the gross tonnage of Titanic. But she and her sister ship Olympic and the still under construction Britannic were the largest ships on the North Atlantic.
Departing to great fanfare on its maiden voyage from Southampton, England to New York in April of 1912, the Titanic set sail with approximately 2,240 passengers and crew aboard. Powered by a combination of 2 reciprocating 4-cylinder triple expansion steam engines and a single steam turbine, the ship produced a total of 46,000 horsepower. With steam produced by 29 boilers, 600 tons of coal needed to be shoveled by hand each day. Offering the highest levels of comfort ever seen in commercial transport, while the Titanic's first-class accommodations and services stole the show, even those travelling in third class, by far the largest group aboard, enjoyed superior amenities than any other ship of the era. Four days into its voyage across the Atlantic, the Titanic received warnings of drifting icebergs from other ships in the area. Not considered a serious threat to a vessel as large and as advanced as the Titanic, the doomed passenger liner continued at its full speed of around 22 knots until moments before the jagged underwater spur of an iceberg struck its starboard side.
The iceberg cut a series of quite small holes into the shell plating of the ship below the waterline. Had those holes been in one compartment, there wouldn't have been a problem. They certainly wouldn't have arrived in New York on time.
Following the collision with the iceberg, the seams of the buckled hull separated to allow 5 of its 16 watertight compartments to fill with water. The ship could only survive the flooding of 4. Although exceeding the safety standards of the day, the Titanic carried only enough lifeboats for 1/3 of its total capacity. And in the haphazard abandoning of the ship, these precious few lifeboats were launched underfilled.
The Titanic tragedy left such a mark on everybody throughout the world, because how could something like that possibly happen? Well, it can, and it did under those circumstances.
"20 years after the sinking of the Titanic, the next big thing in ocean liners took to the seas. 10 years later, it too would meet an untimely fate. Launched in 1932, the SS Normandy was the ocean-going pride of France. With its revolutionary hydrodynamic hull and lavish Art Deco stylings, the ship was heralded as the greatest passenger liner ever created. And featuring an advanced transmission system to address the shortcomings of traditional direct-driving steam turbines, the Normandy remains the most powerful steam turbo-electric propelled passenger ship of all time. Running on more conventional steam turbines, the RMS Queen Mary boasted what is probably the largest powertrain ever built aboard a ship.
In 1931, all work at the John Brown shipyard was suspended for 3 years. Ship number 534, as she was then, sat there rusting for all that time until work was resumed.
A great day for Clydeside. Work is resumed on the Cunard number 534. It is hoped that the liner will be ready for launching this autumn.
It was resumed and she was completed in 1936, having been launched as Queen Mary. She was 1,019 feet long and about 81,000 tons gross. A large, elegant ship and the biggest liner in the world at the time.
With the majority of space on its lower 5 decks occupied by boiler rooms and engines, the combined output of the 4 Parsons steam turbines allowed a whopping 160 horsepower, allowing the Queen Mary to wrest the Blue Ribbon from the SS Normandy in 1936.
Now, after 7 years, the Queen Mary has recovered the honour and arrives at Southampton to be hailed in triumph by Britain. Well done, Queen Mary.
While the Normandy reclaimed the honour the following year, the Queen Mary won it back by setting new transatlantic records in 1938. Records that remained unbroken until the early 50s.
Queen Mary could achieve 30 knots, but the service speed across the North Atlantic was generally about 27 knots. You kept power and reserve in those ships in case of bad weather so that you could make up time, because this was very much a scheduled service. You needed to arrive and depart at the right time. And that's a great speed in those mighty ships crossing the North Atlantic.
Undergoing a successful conversion to military service during the Second World War, the passenger liner cum troop ship survived the conflict unscathed. Often travelling without escort, the Queen Mary simply outran the threat posed by enemy vessels. And during one Atlantic crossing with over 16,000 American servicemen aboard, she set another record: most passengers ever transported on a single vessel. The rise of affordable and fast jetliners changed ocean-going travel forever. Unable to compete on speed or economy, passenger liners needed to offer something that air travel could not. This is what they came up with: the MS Oasis of the Seas. The first of the Oasis-class cruise ships, she, along with her 2 sisters, represent the largest passenger ships in the world.
Amongst the largest cruise ships in the world are the Oasis-class cruise ships, which have recently been built, and they're 225,000 gross tons, which is a very large ship indeed, with a very large passenger carrying capacity.
With 16 passenger decks, the Oasis towers 72 metres above the waterline. Powered by a combination of 3 16-cylinder and 3 12-cylinder marine diesel engines, the Oasis pumps out over 130,000 horsepower. These engines not only drive the 3 electric azimuth thrusters for the ship's propulsion, but provide electricity for its lights, elevators, water treatment plant, and all other systems needed to keep the residents of this floating city comfortable and entertained. Seafaring on this scale poses a big engineering problem. With rough seas capable of battering vessels from all sides, megaships like the Oasis class are subjected to even greater stresses as its gargantuan structure faces uneven strain across the uneven water. The Oasis withstands these shifting stresses not by force, but by calculated give and take. With its cage-like internal framework allowing a significant amount of movement, the Oasis, like all big ships, constantly bends, sags, and twists by design. Spread across the entirety of its megastructure, the degree of movement in this surprisingly limber vessel is barely perceptible to those on board. Not everyone on the water is content with pleasure cruising, and the need for speed has had as powerful an influence on sea travel as it has on travel through air and on land. With water imposing greater uncertainty and greater resistance in the form of friction, The quest for speed here is not only difficult, but dangerous. Of those brave or foolhardy enough to launch an assault on the water speed record, over 3/4 have lost their lives. By 1930, with official rules set, the water speed record had become a source of national pride, hotly contested between Britain and America. This boat, the Miss England II, was to claim the honour for the Brits, but at great cost. With a twin-bladed screw propeller powered by twin Rolls-Royce V12 air racing engines, the Miss England II featured a single keel with a stepped hull to reduce friction and drag. With longitudinal notches running beneath the hull, as the boat gains momentum, these steps create a suction effect, drawing air in from the sides to generate lift. Raising the boat to reduce the wetted surface area, the area of the boat in contact with the water, stepped hulls improve efficiency, allowing more speed with less horsepower.
As a powerboat goes faster, if the design is in such a way that you can actually use some of those hydrodynamic forces, such as a very large surface for planing, when the water actually hits that surface, it gets deflected downwards and can actually make a significant vertical hydrodynamic force and literally lifting the entire boat out of the water in the same way that we talked about with the hydrofoils.
On the ominous date of Friday the 13th of June 1930, pilot Sir Henry Seagrave, along with his mechanic and chief engineer, set out on Lake Windermere to chase down glory. During 2 successful runs, they averaged a speed of over 85 knots, nearly 160 kilometres per hour. With a new record in hand, the third run sought to push the average even higher, but ended in disaster. With the boat thought to have struck a floating branch, when the spray from the crash cleared, the engineer was dead. While the mechanic survived with a broken arm, Seagrave regained consciousness just long enough to ask the fate of his men before dying from acute lung injuries. Salvaged and repaired, the boat itself went on to set new water speed records throughout the early 1930s. But as the race continued, it was to be rendered slow by a new breed of speedboat. In 1955, this boat, the world's first successful jet-powered hydroplane, started a revolution in speed. The British-built K7 Bluebird reigned over the water for more than a decade, setting 7 world records and adding nearly 160 kilometres per hour to the target. Nicknamed the Blue Lobster for its forward set of stabilising sponsons, the K7 Bluebird was representative of the departure from single-keel speedboats to a 3-pointer hydroplaning design. Operating on the same principle as a hydrofoil, at speed, the Bluebird generated sufficient lift to raise the majority of its hull out of the water, minimising drag to maximise speed and efficiency. Constructed with a lightweight aluminium body, the K7 was built around an ultra-rigid steel frame and powered by a Metropolitan Vickers Barrel turbojet engine that produced a whopping 16 kilonewtons of thrust. Developed by British speed demon Donald Campbell, the first person to set both land and water speed records in the same year, the K7 was both his glory and his downfall.
Once you start going at these very, very high speeds, a very small change in that force balance could create quite a catastrophic change in how the boat's going through the water.
Modifying the Bluebird constantly throughout his career and piloting it to even greater speeds, it was in the bid to set his 8th water speed record that Campbell paid the ultimate price. With his sights set on being the first to break the 300-mile-per-hour mark, a goal that meant increasing his current record by over 40 kilometres per hour, Campbell took to Coniston Water in the English Lake District in 1967. Now under the power of a lighter and more powerful Bristol Siddeley Orpheus engine boasting 20 kilonewtons of thrust, Campbell's initial run was just below his 300-mile target, averaging 479 kilometres per hour. His second dash was even faster. But when travelling at an uncharted speed of over 510 kilometres per hour, the craft began lifting from the surface, ultimately going beyond its critical pitch and taking off from the lake before cartwheeling to a violent stop. Campbell was killed instantly. Above and below the surface, the sea is a world of extremes. To carry us further on and deeper into the sea, we have to develop vessels that are equally extreme, penetrating some of the most inhospitable places on the planet.
The ocean surface is ever-changing, and it creates an environment that I would suggest as a naval architect means that putting structures into that environment that is one of the most challenging engineering opportunities we have as modern scientists and engineers.
Icebreakers are among the most robust vessels on the sea. Operating where others fear to tread, they clear the path for merchant vessels needing to transport cargo through frozen trade routes, as well as conducting research missions in Arctic and Antarctic waters.
Suppose the sound of a ship breaking ice at speed is like living inside a coffee grinder or something. It's incredibly loud, and it's accompanied at the same time by the motion of kicking back and forth, because even if the ship is going fast and breaking ice very efficiently, it's still being buffeted. And you can feel it. You can feel it, and it's intense.
Since the age of sail, ships operating in the polar regions have been built with various measures to combat ice. But the modern steam or petrol-driven icebreaker took shape in the early 20th century. While design has continued to evolve and breakthroughs, both literal and figurative, continue to be made, perhaps the most significant advance was the incorporation of nuclear power. Launched by the Soviet Union in 1957, the MS Lenin was not only the world's first nuclear-powered icebreaker, but the first nuclear-powered surface vessel. Raw power counts for a lot when coming up against a substance with roughly the same tensile strength as concrete.
Crunching and crashing her way through the frozen Arctic, the Russian atom-powered icebreaker Lenin was on an unusual assignment.
And the ability to run continuously for years without refueling is a great advantage when operating in some of the most remote regions on the planet. Today, the nuclear-powered variety of icebreakers remain the most powerful, and all of them are Russian. In terms of design, for icebreakers, hulls are everything. Built with double hulls to ensure integrity against the increased loads placed upon them, they are constructed with a particular grade of steel, resistant to brittle fracture in extremely cold temperatures. The sloping shape of the icebreaker's bow allows it to be driven up on top of thick ice, where the weight of the ship presses down to break it apart. Also in the icebreaking arsenal can be a bubbler system, which forces compressed air through holes in the bow to form a cushion of air between the ship and the ice. If the ship becomes trapped, a healing system can be used, pumping tons of water from one side of the ship to the other in order to rock it free. And with abrasion-resistant coating, the last job of the icebreaker's hull is to safely clear broken debris, forging a path for others to follow. The crushing, pitch-black waters of the deep sea remain the least explored region of our planet. And the safest, most efficient way of venturing to these mysterious depths is with unmanned craft. Remote operated vehicles, ROVs for short, represent a new breed of sea power. Considered the Swiss Army knife of underwater robots, ROVs have applications in everything from surveying wrecks to military mine hunting.
Tethered systems have a wire going back to a control, and the person controlling it will look through a camera or a sonar system and then detect, see what it is, and then they'll make the decision what needs to be done and they'll bring it back.
By far, the greatest use of ROVs is in scientific research, shining a light into some of the planet's most challenging and poorly understood waters. Operated by the US-based National Oceanic and Atmospheric Administration, the Deep Discoverer, nicknamed D2, is a cutting-edge ROV, bringing us closer than ever to the mysterious biology and geology of the deep sea. Operating in tandem with a camera sled unit serving to illuminate the D2 and provide a wide-angle view for the topside pilots, the Deep Discoverer is connected to its launch ship by an umbilical cable. Neutrally buoyant, this cable effectively separates the ROV from the motions of the ship whilst powering the D2 and instantly transmitting its data back to the surface. With its high-definition camera and specialised robotic arm for sample collection, D2 is providing scientists with a clear look at environments that have never been seen before. Constrained by their connection to a ship and the stamina of their human handlers, ROVs provide a detailed but limited picture of the ocean. But it is autonomous underwater vehicles, AUVs, that offer a broader understanding of the vast marine world. Once programmed for their long-range missions, these vehicles are let loose, returning to base on their own once the assignment is complete.
When things are under the water, radio waves don't transmit under the water. So you either have to use sound or they have to be pre-programmed and they'll come up to the surface and then do a radio transmission or go back under, and that's where autonomy is really important. So it gets told what it needs to do and it can make decisions while it's down under there.
While AUVs are in keeping with the trend toward autonomous craft in the air and on the roads, in the aquatic environment, a greater degree of engineering challenges needed to be overcome. The first was communication. With radio waves unable to travel very far through water, unmanned underwater vehicles had to get smart.
When they detect something or on their preset pattern, if something's in the way, it can then make a decision to reprogram itself for what search pattern it needs to go on or what it needs to look for. So it has a limited level of artificial intelligence.
Travelling without GPS and with minimal contact with human handlers, AUVs navigate via sonar or dead reckoning calculations, with many changing their mission profile in response to the environmental data they collect and analyse. The high drag inherent in water means that propulsion is another challenge. Typically running on long-range electric motors, AUVs tend to employ efficient propellers, often with ducted quart nozzles. For even longer stints at sea, underwater gliders use their aerofoil wings to convert the vertical motion of repeated ascents and descents into horizontal propulsion.
They can either look like an aircraft or some of them look like just simple torpedoes. they have a device in there that simply changes the buoyancy from one end to the other. So it just pumps a little bit of liquid in a tube forward and back. What that does is change the buoyancy of the system so it starts to sink. So this thing will dive down. When it gets to a set depth, it changes the buoyancy back and it just comes back up. So it's actually gliding in the ocean.
Innovating to meet the challenges imposed by the sea, AUVs are at the forefront of the modern quest to better understand the ocean.
Part of their mission is to go to places we haven't been before, to help us collect data that we haven't been able to collect in the past, to collect samples that we don't already have, and to fill in our understanding about how things look, what their history is, why they work the way they do, and what the future holds.
And the innovations do not stop with the sea. The technology developed here is powering travel beyond the waves and beyond the planet. A planet-detecting satellite launched in 2009, the Kepler spacecraft's mission was to monitor the brightness of distant stars within the Milky Way. With its high-powered photometer, Kepler was set to keep watch for the periodic dimming around stars that would indicate the orbiting of potentially Earth-like planets outside our solar system.
What is really cool about this telescope is how it's actually controlled in space. It is literally floating through space. It is being steered through space like a sailboat.
Aiming and stabilizing its photometer via a series of 4 reaction wheels, when 2 of these wheels jammed, the mission was on the brink of failure. But one radical idea offered a solution, a concept first dreamed up by the 17th century astronomer for whom the Kepler spacecraft was named. By harnessing the power of solar winds, the pressure exerted on spacecraft by photons within sunlight, the Kepler could be stabilized against this force.
We point Kepler at a direction of the sun so that as the wind comes from the sun, it keeps it in spot and keeps it pointing. So as Kepler moves around the sun, we keep pointing it so that sail is pointing at the wind of the sun.
It was harnessing the solar wind that steadied this craft, allowing it to continue its planet-hunting mission. While the Kepler became a solar sailboat out of necessity, spacecraft like the light sail are doing it by design.
So this is a giant satellite that's going to deploy a sail. They want to point the sail at the sun, and when a big burst of wind comes from the sun, push it, and that will accelerate the satellite through space.
The light sail aims to be the first controlled solar sail in the Earth's orbit, testing the viability of the technology for transporting scientific payloads, potentially even human passengers, through space. Launched by conventional rockets, once in space, the light sail unfurls its 32 square meters of reflective mylar sail. As the photons of sunlight continually hit and bounce off the sail, they transfer their momentum, propelling the spacecraft in a similar manner to a sailboat on a sea. But unlike the water, the vacuum of space offers no resistance to movement, and a solar sail is able to constantly accelerate, theoretically building speeds 5 times faster than rockets.
In space, there's nothing to stop you. So once you're going, there's no air, there's no wind. So if you can get a burst of speed, 20% the speed of light, you can get a satellite that goes through space 20% the speed of light. So we can actually have interstellar travel in only a few decades with the same technology and same style of boat goes through the ocean.
Reimagined, the ancient engine that is the sail is set to gracefully carry us further than ever before, opening the door to new galaxies. Power. Brute power, belching from a smokestack. Or roaring from a diesel. The power to cross continents, move armies, destroy distance. Artists, writers, poets, everyone seems to have found the greatest fascination and the greatest romance in the powerful engines they have watched cross bridges, climb mountains, and drive through the heart of cities. The romance of trains. The story of rail travel is the story of huge loads, extravagant luxury, and astonishing speed. For century after century, the power to move ourselves, our goods, our crops, our armies was generated by our own muscles or the animals we could harness. And then came steam. In this episode of Power, we explore the greatest steam engines that crossed continents and tell the story of how the rails, bridges, and tunnels on which they ran changed the world. This is the story of rail power. The steam locomotive. Wherever it ran, stopped enthusiasts and small boys in their tracks in its heyday and still exerts a very special appeal. Perhaps more than any other machine, the steam locomotive says power. The Bayer Garrett 6029, a workhorse loco from the 1950s, was manufactured in Manchester, England for heavy goods service. Number 6029 pulled its loads around Eastern Australia for the New South Wales government. And fully restored is the largest working steam loco in the Southern Hemisphere.
The Bayer Garrett is 265 tonnes fully loaded. Fully loaded includes 40 tonnes of water. Now, this locomotive burns through 430 litres of water a minute. So to go anywhere of a reasonable distance, it needs a lot of water. Also needs a lot of coal. It goes through 37 kilos of coal a minute at full power. In fact, it goes so quickly through the coal that a fireman couldn't shovel it fast enough. The draft is so strong in the fire that it would suck the shovel out of the fireman's hand. And so it has an automatic stoker to draw the coal through from under the tender, to pulverise it on the way through, and then jets of steam are used by the firemen to fire it round a firebox, the grates which are the size of nearly 4 grand pianos. And so everything's on a massive scale. And you get up in that cab and it's almost intimidating how big this machine is.
In service for 20 years, the 6029 incorporated the most modern technology of its time, hauling export coal to the ports, or concentrate from the mines, and goods from all over the state.
It certainly has its own sort of personality with its noise. It's so noisy that the drivers have to have loudspeakers placed in the cab. They had to put megaphones in. Going through tunnels, they had to have leather jackets and hoods over their heads to protect them from the heat. It was really out in the fringe. It's sort of like, you know, being an astronaut in our times. You were really riding a big machine.
The power to move mountains or populations is no longer supplied by steam. Modern trains look faster, much sleeker. But the Bayer Garrett remains a formidable expression of power. The first trains to be hauled along rails did not even have the benefit of steam. horse-drawn and man-powered trucks took advantage of the lower friction of pulling loads along rails. Steam brought power to the railways when pioneers like Watt and Trevthick made steam engines practical.
What was going to be the most effective way to move people by rail? Should it be horsepower? Should it be steam power? Should it be this? Should it be that? Should it be dragged by ropes, chains, whatever? But steam, with Robert Stephenson's extraordinary technological advances, with the creation of locomotives like the Rocket, won the day.
The history of steam power stretches back 2,000 years. 2,000 years of development. But the principle of steam power has remained constant. A steam engine uses heat to produce a gas that powers mechanical work. The gas is steam, which is produced by applying heat to the working fluid, typically water. Heat can be produced by burning any fuel. In steam locomotives, typically coal and sometimes wood. The water separated from the combustion is heated in a boiler, where at high pressure it expands through pistons to power the mechanical work. Then, men like Stephenson and trains like the Rocket transformed life, and with bridges, tunnels, stations and permanent way, transformed the landscape.
The Rocket was one of the locomotives that he built of a series that won the Round Hill Speed Trials, which then led to the first public passenger railway, 1830. That led to a revolution. By 1835, Germany had opened a railway, America was opening up, 1837, Russia, on it went. The railway age and the railway revolution changed the world.
The Rocket seems to us today to have been a rather ambitious name. Its maximum speed was 45 kilometres an hour. At the time, such propulsion seemed beyond reckless, but people survived the journey, and the age of rail was born. Trains were first made to carry freight to compete with the canals. The first lines brought power to horse-drawn railways or tramways that had been hauling tin or coal or iron out of mines. But with the Industrial Revolution and the migration to and growth of the cities came a mobile population. And the beginning of the story of famous trains, romantic names like the Flying Scotsman.
The Flying Scotsman's probably one of the most iconic steam trains ever built. 1923, the early 20s, we're seeing the golden age of railways, and particularly steam traction. And you have one of England's great designers, engineers, Nigel Gresley, coming up with a design that sets a new benchmark for steam passenger locomotives.
The route was operating by the 1860s, but the name was not attached until 1923. 630 kilometres, linking the Scottish capital Edinburgh to London. The Flying Scotsman is a name that had been carried by some of the most powerful steam locomotives and is carried today by their modern successors. The classic Flying Scotsman, the first loco to carry the name, is the LNER, London and North Eastern Railway, Class A3. Built in 1923, the first steam locomotive to officially reach 100 miles an hour, 160 kilometres per hour. With a coal capacity of 9 long tonnes, the A3 could complete the journey without refuelling, and was retired from regular service in 1963, having clocked up more than 2 million miles, 3,220,000 kilometres.
Romantically, but certainly from an engineering point of view, the Flying Scotsman remains an icon, a symbol of progress.
the most famous of them all, the Flying Scotsman, the epitome of all that a massive steam engine should be, noble, powerful, fast. A champion bearing the torch for an age that will never come again.
But it's another LNER locomotive, the A4 class, a 462 bogie arrangement that followed the A3 into service in 1938, that best captures the power and romance of steam. Particularly an engine named Mallard. Wind tunnel tested and aerodynamically designed, the Mallard was intended to haul high-speed trains and still holds the world record for a steam locomotive, 200.4 kilometres per hour, which was perhaps the limit for steam. The Mallard had a 3-cylinder engine and repeated problems with the middle cylinder overheating. To alert the driver to this problem, a stink bomb was fitted to the middle cylinder, which popped on overheating, alerting the driver through the offensive smell of hot aniseed oil. And the bomb went off shortly after Mallard broke the record. Neither as fast nor as streamlined as Mallard, but significantly more powerful, and with an appearance that totally justifies its name, is this North American steam locomotive. This is Big Boy. The 4000 Class 4884 articulated Union Pacific monster of the 1940s. The only locomotives to feature the 4884 arrangement, which gave stability negotiating curves.
The Big Boy in America just makes the ground shake when you think about the zenith of rail technology because of the size of the thing. And nothing has beaten the Big Boy in size or scale.
Big Boy was designed to haul freight over the Wasatch Mountains between Wyoming and Utah. To get the job done, Big Boy, where the A3 Flying Scotsman had a coal load of 9 long tons, had a fuel capacity of 25 long tons and a water capacity of 95,000 litres, firing up a 4-cylinder engine that could haul massive loads at up to 130 kilometres per hour. Firing up boilers was a common characteristic of steam locomotives. But not all coal is the same. Big Boy's operator, Union Pacific, owned the mines that supplied the coal that fired the boilers. But it was low-grade bituminous coal, more needed to be burned for the same effect, so Big Boy was fitted with extra large grates. The sight, sound and smell of the steam locomotive was fundamental to building the 20th century. But as the century wore on, its days were counting down. Cheaper, less labour-intensive and more efficient, the diesel and diesel-electric power plant was taking over.
And so in the 1940s, you saw advances all over the world in the implementation of diesel engines into locomotive traction, signalling the end of the steam era. Probably a lot quicker than many people would have expected, because the steam power was such an important part of everyday life at the time. However, diesel technology and the advances allowed for great savings in the labour that it took to fire up a steam locomotive and operate a steam locomotive, and in speeds and traction effort and in efficiencies that could be achieved in running trains.
But in some parts of the world, steam still has a place. The earliest of the power plants that we have looked at. It was built in England in 1855. This is living history. This is the Ferry Queen. Producing 97 kilowatts of power and a maximum top speed of 40 kilometres per hour from her two-cylinder engine, the Ferry Queen was in service hauling troop trains during the uprising of 1857, which to Indians is the first war of independence and is known in British history as the Mutiny. By comparison with the mighty Mallard and Big Boy, Ferry Queen carries 2 long tons of coal and 3,000 litres of water. The Ferry Queen continued in regular service into the 20th century, was withdrawn, rediscovered, restored, and now hauls a luxury train regularly between New Delhi and the Rajasthani city of Alwar. These, then, are some of the locomotives that powered the spread of the railways. We look next at how those rail networks, spreading across different parts of the world, powered global change. In Russia, that spread of railways was vital to stitching together the furthest reaches of the largest land empire in the world. In Europe, the spread of railways through the Victorian era required some sort of planning. The timetable was invented, and with the timetable, for the first time, came the need for clocks in different towns and cities to be synchronized. But it was the speed with which railways allowed young countries to develop not just their industrial strength, but their sense of common identity that most powered the growth of Australia, of Canada, and of the United States. Over 250,000 kilometres, the track length of the US rail network is the longest in the world. Perhaps most astonishingly, that comprehensive crisscrossing of the country had been achieved before the end of the 19th century. The last spike ceremony joining the continent from sea to shining sea by rail was driven in 1869. 5 days later, the Continental Express departed New York, and 4 days later, ended a journey that, with frequent changes of horse, had previously taken months. It arrived in San Francisco. In the great age of steam, American coal and wood-fired locomotives, with their pointed cowcatchers or pilots, so familiar from so many Western movies, opened up the States. And many made and many lost large fortunes building railroads. The famous locomotive, the General, is an outstandingly restored example of the type. Built in 1855 and finding fame during the American Civil War as the engine stolen by Union spies endeavoring to cripple the Confederate rail network, the General hauled passengers and freight for the Western and Atlantic Railroad before the war and continued in service into the 1890s. The General and the similarly specified William Crooks remind us today of the pioneering age of American railroads. In its golden age, travel around America by rail inspired a folk culture and countless popular songs romanticizing about the Chattanooga Choo-Choo, the Atchison Topeka and the Santa Fe, Pullman trains and the A-Train.
So people like George Pullman, who developed new ways for people to travel in comfort and style. For goodness sake, the Orient Express and Pullman's amazing series of parlour cars that he built at huge expense, which changed the way we travel and became synonymous with what you would consider to be, oh, I'd love to fly to London business class. Well, that's what people were saying 150 years ago. Oh, I'd love to travel by Pullman.
With the spread of the motor car, the development of highways and the affordability of flying, the railways in America suffered.
Days of the railways are over. Nah, she's all over, mate. Done and dusted. Trains are finished, particularly in America where the oil companies rule sway, and trains are on the nose. They're out of fashion. And the great name trains of America were wound down and ceased to exist.
But by adapting to new markets and new technologies, they have powered back. Across the United States border, Canadian railway engineers had the same ambition, to link their country coast to coast. They faced particular challenges from the landscape and the climate. Historian George Stanley wrote in The Canadians, without railways, there would be and could be no Canada. A fact recognised by the authors of Canada's Constitution Act of 1867, a condition of which was the building of the intercolonial railway. But the proposed line, 1,600 kilometres longer than the first US Transcontinental, represented an enormous expenditure for a nation of only 3.5 million people. Construction began in 1881, and the last spike was driven on the 7th of November 1885. The first passenger train left Montreal in June 1886, arriving in British Columbia on the 4th of July. Completion of the railway was one of the great engineering feats of the day. The Canadian Pacific Railroad had a profound effect on the settlement of the West, and new cities, from Winnipeg to Vancouver, were heavily dependent on the railway. Some of the engineering feats that had to be overcome, crossing mountains and traversing Kicking Horse Pass, were extraordinary. Though it is not the Canadian Pacific, but another route in North America, a remote and isolated railway that best expresses the engineering power that has driven railways into almost every part of the planet. The White Pass and Yukon is a route that doesn't link to any other railway. It runs between Skagway in Alaska and the Yukon. Built in 1889 to service the Klondike Gold Rush, the line is testament to the power of railways to transform country and of men to create railways.
The old-timer at the station gives the passengers a send-off on their 110-mile trip. The first 20 miles carries the train 3,000 feet into White Pass, where so many fell and died trying to conquer the mountains and cross over into the gold country.
Considered an impossible task, tens of thousands of men and 450 tons of explosives literally blasted the White Pass and Yukon through coastal mountains in only 26 months, creating a spectacular engineering achievement that climbs more than 900 metres in just 32 miles and features steep grades of up to 3.9 degrees, 2 tunnels and numerous bridges and trestles. There were very few such obstacles facing those joining the two coasts of another continent. As its name explains, Australia's Transcontinental Railway joins the Indian and the Pacific Oceans. The Indian Pacific.
In Australia, 80% of our freight is moved by rail. And nothing is more efficient than a steel wheel on an iron road.
The great interior of the island continent of Australia is arid, has poor soil, and is sparsely populated. The coastal margins on the Pacific coast in the east and the Indian Ocean coast on the west house the great majority of the Australian population. For many decades, travel between these two developing centres of population was almost exclusively by sea. And then, they built the railroad. Distance and remoteness, rather than challenging physical obstacles, were the main problems that the builders faced. And it was power that asked one of the most difficult questions. How is a train journey that will take several days to be maintained, fueled, serviced, as it crosses an empty landscape? A landscape so featureless that it crosses a plain called Nullarbor, from the Latin for no trees, and so flat that it has the longest dead straight track in the world, 478 kilometres. When the lines advancing from the east and west were joined in 1917, the answer to the supply requirement was the construction of a number of railway halts, less than settlements, small maintenance depots where tiny isolated communities would exist to maintain the tracks and stockpile the water and fuel that the Indian Pacific needed to complete its journey. The train runs now, linking Sydney and Perth, and is very popular with tourists and those wanting to see the big country. But almost all of the halts are deserted now as the diesel locomotives cross the continent. Almost, but not quite all. In most countries, as railways have spread, engineers have faced challenges.
Progress reports on the tunnel under Mont Blanc. It's a two-way task. Here are Italians tunnelling from their side, and a pretty dirty job it looks. They started about 3 years ago and have not yet gone 2 miles into the mountain.
Not everywhere is like the Nullarbor Plain. To allow the locomotives to power across the landscape, bridges and tunnels of often extraordinary ambition have added to the story of rail. Of course, wherever tracks were laid, one fundamental principle had to be understood: how to keep the train on the rails. Whether steam or some other power source, the question, as trains get heavier and faster, is what keeps them on the rails? Train wheels are restricted horizontally by the flange on the inside of the wheel, which bears on the track, keeping the wheel from moving towards the outside of the track. But this flange is not enough to keep a train on the rails. Train wheels aren't perfect cylinders. They're beveled to make them wider on the inside. The wheels are connected by a fixed axle, meaning that the wheels on both sides of the train always turn at the same speed. This can present problems when turning because one wheel has to cover more distance than the other. Most vehicles solve this problem by decoupling the wheels, but unlike conventional automobiles, trains do not have a differential. So how do locomotives stay on a bending rail? What keeps them on track is the conical nature of the wheels, with the outer portion narrower than the inner. The conical edges help in translating angular velocity into different linear velocities. A train that can be as long as 3 kilometres, hammering along at speeds of up to 110 kilometres an hour, creates quite significant problems. One is drag, because drag literally drags down fuel economy. So aerodynamics is important to the operation of freight trains.
So certain ways that you can look at improving drag on intermodal freight trains is to look at how you stack them. So you often see very large gaps in the stacking of these wagons and the loading of them. So if you can optimise that, then it's quite possible to reduce the actual drag and therefore the energy used when you're transporting goods.
Freight trains frequently travelling long distances across exposed landscapes are often exposed to high crosswinds.
Those side forces can cause an interaction between the track and the wheel, and that can lead to increased friction, which then feeds into fuel economy. So it increases the actual frictional load, and that can be very significant if it's not detected.
In heavy winds, it is also not uncommon for containers to be blown off of trains, which can result in damage to the track as well as damage to the goods.
One of the challenges in loading a freight train is that quite often you've got containers of different shape and sizes, and you've also got wagons that carry those containers, and they're often of different shapes and sizes, and you've got to put them all together a little bit like a jigsaw puzzle and come up with a finished product. And sometimes that even involves stacking the containers on top of each other so that the train can be double stacked.
By optimising the layout of the train and spacing, fuel efficiency savings can be as high as 10%. The Hawkesbury River Bridge. North of Sydney, Australia, the Hawkesbury River flows through Broken Bay to the sea. For many decades, passengers travelling north left their trains on one side of the Hawkesbury, crossed the river by paddle steamer and connected with a train waiting on the further shore, an inconvenience replicated in many places around the world, and the reason why so many of the great engineering feats from the 19th century onwards are railway bridges. The bridge across the Hawkesbury is an example. The present bridge, the second, was built to replace the first, which had been built by the Union Bridge Company of New York in 1886. The second bridge was completed in 1946. Its 3 spans, standing on piers sunk 56 metres into the riverbed, a total length of 890 metres. Significant, but dwarfed by other bridges around the world. The longest structure that carries trains is the Great Belt Link in Denmark. A combination of bridges and tunnel linking islands across a length greater than 6.5 kilometres. The Great Belt Link joins islands. The Channel Tunnel joins countries. There are bridges and tunnels in many parts of the world that cross borders, but the Channel Tunnel is unique. It fulfills a dream that goes back well over a century, of allowing traffic to move between the British Isles and the continent of Europe. The engineering feat involved is prodigious. It has the longest undersea portion of any tunnel. It is the 3rd longest railway tunnel and the longest international tunnel. The pursuit of speed and comfort has transformed rail travel in many parts of the world. Seemingly destined to obsolescence by road and air travel, railways have rebounded strongly with very fast services, and Eurostar is an example of such a service. Taking passengers from the middle of one capital city to the heart of another with speed, comfort and convenience competes more favourably with other options. The Eurostar, formerly the British Rail Class 373 or French TGV TMST, Trans-Manche Supertrain or Cross-Channel Supertrain, run up to 300 kilometres per hour with a top recorded of 334.7, drawing power via pantograph from electric overhead lines and delivering power through sets of powered axles in each car. Each set generating 12 megawatts of traction power and having the lowest power-to-weight ratio in the TGV family of trains. Each Eurostar has a number of special safety features to minimise issues that may arise during the traverse of the tunnel. The braking system, for example, is capable through a combination of disc brakes and rheostatic braking, a form of dynamic braking in which the electrical energy produced by the motors is dissipated as heat by a bank of onboard resistors, bringing the entire train travelling at 300 kilometres per hour to a standstill in 65 seconds. When trains power out of tunnels, there are places in the world where they encounter conditions that could stop them on the tracks, which is why much ingenuity has been applied to the problem of extreme weather. China has built a high-speed railway network which accounts for more than 60% of the world's total. Some of it reaches into exposed and inhospitable landscapes. In Xinjiang, a region with an arid climate, the railway passes through 4 major high-wind areas using a high-speed train based on Japan's Shinkansen that can operate in temperatures as low as -40 degrees Celsius and at altitudes as high as 3,600 meters. Some of the high-speed lines operate in very high wind zones, where crosswinds can prevent trains from operating because of the danger. Trains in such regions monitor the winds and sometimes will stop in sheltered zones and resume operating when the winds die down. but designers are reluctant to allow wind power to interfere with the power of the train.
Part of what we're looking at is the design of the train, or the forces that the train is going to experience associated with its geometry. So, how the geometry interacts with the crosswind flow. But also important is, whether there's a requirement for some sort of fence along next to the trains to mitigate the winds, whether the embankment that the train might sit on, how that should be designed to reduce the load and the risk of the train blowing over.
In different countries, less harsh, but still potentially crippling winter conditions are countered by point heaters to prevent points from being frozen, and by landslide snow fences, which in countries like Japan and Canada prevent drifts from falling across the track. Where snow does block the permanent way, other solutions must be found. The rotary snow plough. A Canadian invention, the rotary plough made its first appearance in 1869. Since then, it has been throwing snow off tracks with great efficiency. The rotary plough improved on the wedge plough, the first mechanised device for clearing tracks. When the wedge found the going too tough, the snow too deep, the rotary could push a way through. The rotary snowplow is pushed by one, or conditions requiring it, two locomotives. A motor inside the plough body, originally a steam engine, later diesel or electric engines, rotates the circular assembly. The snow dislodged by the spinning blades is forced back behind the cutting face and out through a channel behind the disc, then thrown through an output chute. The chute is adjustable, an operator behind the blade assembly being able to direct the output left or right and also control the speed of the blade. Expensive to maintain, snow ploughs have now been largely superseded with flexible blade ploughs, pushed by powerful locomotives capable of dealing with all but the most extreme winter conditions. The power to haul the train, the equipment to keep the track clear, the engineering to join countries and continents is all about one thing: the power to travel. A foreign correspondent once complained that flying was not travel. It is, he said, effecting a positional transfer. But every time we board a train, we go on a journey. Steam is at its most romantic in some of the famous trains that steam locomotives have pulled through exotic landscapes, such as the toy train. A legendary 78-kilometre narrow-gauge railway between New Jalpaiguri and Darjeeling, 2,000 metres above it in the Himalayas.
The lower Himalayas in the distance are being revealed, leading up to the township of Darjeeling itself, which unfolds as classic British architecture in parts, and these sweeping views of the mountains. It really is one of the great train journeys of the world.
Between 1879 and 81, the British built the line that is now a UNESCO World Heritage Site. Escaped to the hill stations when the heat of the summer was at its worst, and the suitability of the area for tea growing made construction a viable proposition. The steam locomotives in use, some updated with oil firing, are B-class design and date back to the late 19th century. Diesel engines are also in use. But it is the B-class locomotive, known as the saddle tank loco, that most perfectly captures the romance of the bygone age.
It hits the part of town where the railway is in the main street, on the main road to Darjeeling. And so the train is rattling along with two guys sitting on the front of the locomotive with red flags, telling people to get out of the way, and there's all sorts of negotiating of the train with traffic and passengers and pedestrians in a way that only India can do.
Where other locomotives we have considered carried many long tons of coal, the engine of the toy train weighed only 14 long tons. But they were far from fragile, and two, Tusker and Victor, are still shuttling up and down the mountain. The UNESCO-listed Kalka-Shimla railway line ran up to the British Hill station north of Delhi. Because it was the seat of government during the entire hot Delhi summer, Shimla was very important to the British, and so was the little train.
Interestingly, the railway's very, very popular today. It's one of those sort of honeymoon destinations. So the train is often full of honeymooners and young lovers. The scenery is astounding, and the engineering and the different climate zones that the railway travels through as it rises all the way up to more than 2,000 metres.
But engineering the line was not without its challenges. More than 400 bridges, all stone-lined, wonderful multiple arched aqueducts, and more than 90 tunnels stand today. A testament to extraordinary engineering skills. Getting up and down mountains has posed an engineering problem in many parts of the world, where friction, traction and gravity have not always worked together.
Because it's steel on steel, trains are much more limited to the angles that they can climb up and down. And that's just because steel on steel has got a much lower friction than rubber on a road.
Various systems have been invented for keeping the train on the tracks, including the sophisticated rack and pinion system on Swiss railways. The rack, the central toothed rail with an appearance similar to that of teeth on a gear wheel, is engaged on steep inclines, typically 7 to 10 degrees, by lowering the train's pinion, a gear wheel lowered from the locomotive when the gradient requires it. With rack and pinion mesh, it prevents the train from slipping on the rails. There are a number of different designs for both rack and pinion, but the principle is constant. Teeth engaging from a pinion on the locomotive onto the fixed rack rail.
The ratcheting systems are just a way of overcoming the metal on metal. So you've got a set of cogs, and the cogs are what provides you the forward momentum, rather than the metal sliding on metal.
There are rack and pinion railways around the world, in addition to the many operating in Switzerland. Three times a week, a train pulls out of the main station of Chongqing, southwest China, on one of the longest journeys in the world. 11,179 kilometres through 5 countries to Duisburg in the west of Germany. The trains, which are 2 kilometres long, reach Germany in just 13 days, reviving ancient trade routes with modern efficiency. Most of the cargo on the trains, with up to 50 40-foot containers, comprises laptop computers, of which Chongqing is the world's largest producer, with 25% of global output. This is the New Silk Road, named after the route in the 2nd century BC that took Chinese goods to the Middle East and Europe. If ever the journey is opened up to passenger traffic, it will surely be one of the great travel experiences. Around the world, there is strong competition in the growing market for train travel experiences. The luxury train that bisects Australia, north to south, offers insight into both a dramatic landscape and a unique culture. The Afghan Express, as it was originally called, the GAN, was named to honour a particular group who played a major part in opening up the interior of Australia.
The interior of Australia was dependent upon camel trains. These camel trains, using camels, imported from Afghanistan mainly, were driven by and led by people from Afghanistan. So when the train became a reality, it was named the GAN in honour of the Afghan camel drivers who had been the only means of transport for a lot of the inland areas of Australia.
The GAN links the southern city of Adelaide to the tropical northern city of Darwin. A journey of almost 3,000 kilometres through the red centre of Australia and the iconic Central Australian city of Alice Springs. The Alice was originally the northern terminus of the route, which was initiated in 1929. The line was not extended to Darwin until 2004. Diesel-powered, the GAN pulls 30 carriages at a quite leisurely pace.
The track now, from Adelaide to Darwin, is almost 3,000 kilometres. Clearly, though, if it takes 54 hours, they're not travelling at huge speeds.
The train averages 85 kilometres per hour and takes 54 hours to complete the journey, and it weighs 1,400 tonnes. Passengers get to enjoy the view, the food, and the odd stop along the way. A train travels through Mauritania in Western Africa, fringing the Western Sahara. It has some similarity to the GAN, crossing an arid, sparsely populated landscape. But the contrasts are great. Like the Silk Road trains from Chongqing, the train in Mauritania carries chiefly freight. It carries iron ore, and with between 200 and 210 cars of 84 tonnes of ore each, they are among the longest and heaviest trains in the world. As mineral resources of the region are further developed, more and possibly bigger trains are going to travel the 704-kilometre line. Hauling the cargo takes 3 and often 4 locomotives capable of operating in the region's searing heat.
So trains might often need 6 engines just so that they can get the train and the rest of the carriages up to the speed required, and also, more importantly, to make sure that they can stop. More often than not, it'll probably be the stop-in requirements of the train that drive the number of carriages. Just because once a train is moving, it's got a certain amount of inertia. You need to be able to put enough power into the braking system such that you can stop the train and overcome the inertia.
The SD70 ACS engine is used, as it is in similar parts of the world, including the Arabian Peninsula. The American company EMD, Electromotive Diesel, manufactures the equipment with a diesel-electric power plant producing 3,400 kilowatts. Variants operate the longest ore trains. Between the iron ore ranges of Western Australia and the port facilities, where the record was set by a train that stretched well over 7 kilometres, had a gross weight of almost 100,000 and was pulled by 8 locomotives. Now that is power. Railways delivered the power to move people, freight, armies, raw materials, the power to move huge loads, and the technology to be fast. In this episode of Power, we investigate the high-speed trains that link cities, the futuristic visions of magnetic levitation and pods, and tell the story of engineering marvels from the longest train to the miniature wonderland. This is the story of rail power. Speed. Almost 200 years since trains became familiar intruders on almost every landscape, the sight and sound of steam has become a romantic memory. Replaced by more efficient, more powerful, more reliable, less polluting forms of power. Replaced above all, in the name of speed. This is the Shinkansen, the bullet train. Not quite faster than a speeding bullet, the Shinkansen redefined intercity rail travel for the modern age. Shinkansen is actually the name of the rail network across which the high-speed trains travel.
They decided to build a completely separate railway, and the word Shinkansen means new trunk line, giving you the idea that it's a separate railway altogether.
A network that revolutionised domestic travel in Japan and set the standard for high-speed rail travel in the second half of the 20th century.
More passengers travel by train in Japan than anywhere else in the world. It sells more tickets, about 1 billion tickets a year.
The first bullet trains began their journeys in 1964, linking Tokyo and Osaka. This line, the Tokaido Shinkansen, remains the busiest fast train line in the world. Over the years, a number of different train sets have entered service. The technology has evolved, as has the design. Aerodynamically refined in wind tunnel testing. The current Shinkansen have a maximum operating speed of 320 kilometres per hour, though they could go faster.
Another key challenge with high-speed train aerodynamics is how trains interact when they're passing one another, and also how they enter into tunnels. So the nose shape on trains can be very different, and it depends on how they're going to be used and the environment they're going to be used, because there's a range of aerodynamic effects that are really important in the design of the train. So if you look at some of the trains around the world, some of them seem quite blunt and some of them are more streamlined, like a ICE3, and then others almost have a duckbill type shape, and that's got to do with the environment that they're going to be operating in.
All Shinkansen are electric multiple units, with the most striking of current designs being the H5, the latest of the 700 series that features the duck-billed nose, an aerodynamic shape which reduced the piston effect, the force of air displaced as the train surges into tunnels.
So when a train enters into a tunnel, it can create a very high pressure wave, and that can cause all sorts of problems, and that pressure wave can also propagate down through the tunnel. So some trains are actually designed to limit or reduce that pressure wave. So when you see duck-billed type trains, it's designed for that purpose.
Aboard these trains, 3 classes of comfort speed passengers to their destinations. Grand Class, Green Car, which is the equivalent of business class, and Ordinary Class. Like almost all Shinkansen, the H5 draws power from overhead wires by means of a pantograph. In the context of railway operation, a pantograph is a device for collecting electrical current. The power supply is carried in overhead wires, and contact with the pantograph's metallized carbon strips draws power to the unit's drive system. For low-speed vehicles, trams, slow trains, trolleybuses, the pantograph uses springs and air. Air pushes the cylinder, which raises the pantograph into position. Springs then maintain contact with the wire. For high-speed units, such as the Shinkansen trains, springs are not efficient, and contact is maintained through a pressurized air system that holds the contact in place through constant force. From the 1960s onwards, the very fast train concept has developed on intercity routes in most parts of the world. but it is a very different type of power source that drives the train that holds the record for speed. That record belongs to a train that does not travel on rails. In fact, it doesn't travel on anything. This is the maglev. Maglev, magnetic levitation, uses the principle of magnetic attraction to both lift and propel the trains. Lift removes friction, maintenance is reduced, wheels are not worn out, and speeds can be tremendous. The record stands at over 600 kilometres per hour.
Japan has been developing a magnetic levitation railway for a number of decades now. And interestingly, there is a test track that you can go to see the train rip by once a day at close to 600 kilometres an hour.
There are regular maglev lines in China, Japan and South Korea, with others in development. A maglev system depends on two technologies, the power supply and the suspension. In some systems, a single technology provides both levitation and propulsion. Electromagnets powering an onboard linear motor. But other systems levitate, the suspension system, but do not propel. EDS, or electrodynamic systems, use superconducting electromagnets, or strong permanent magnets, to create a magnetic field, which induces currents in metallic conductors to push and pull the train towards its designed levitation position. Such systems require a separate propulsion source. Some EMS, or electromagnetic systems, can both power and levitate. Onboard magnetic fields interact with metallic loops set into the walls of the maglev guideway. The loops are made of conductive materials, and when a magnetic field moves past, it creates an electric current that generates another magnetic field. Different types of loops perform three important tasks. One type creates a field that makes the train hover about 12 centimetres above the guideway. A second keeps the train stable horizontally. The third is a propulsion system run by alternating current power, where both magnetic attraction and repulsion are used to move the train car along the guideway.
Principle of magnetism, everyone's played with magnets, and they know that if you put the North Pole and the South Pole together, they attract each other. And if you turn them around and you try and put the North Pole and North Pole together, you can't. They push each other apart. And so they use that principle, except they use electromagnets to cause the train to be held in the air.
The concept of the magnet design means that the only source of friction is air, and the result is a smooth trip at any speed. Unlike other attempts at evolving high-speed rail transport, experiments with power systems that have been abandoned. Trains run on rails, that's why they're called railways. But inventors have been attracted by the idea that trains encountering no friction would be efficient, fast, and quiet. We have seen that the maglev effectively suspends the train above the track, keeping it there through magnetic attraction. Hover trains used a similar principle, suspending the train so that the only resistance it meets is movement through air. Instead of magnets, hover trains employed the cushion of air concept that was developed for and is still the basis of hovercraft. The RTV, Research Test Vehicle 31, was a British experimental train. Work started in the 1960s and accelerated when the hovercraft principle was married to a second British invention, the linear motor. Eric Laithwaite began developing the linear induction motor, LIM, in the late 1950s. LIMs provide traction through the interaction of magnetic fields on the vehicle and a fixed external conductor. Such a motor eliminates the need for physical contact with the track, has no moving parts, and so lends itself to the hovercraft concept. In Laithwaite's original design, two sets of windings positioned a few centimetres apart were positioned so that an aluminium stator plate would fit the gap between the windings, the forces pulling one set of windings towards the plate and thus balanced by the opposite forces in the other set. The hover principle ideally requires a smooth surface so that the cushion of air contained by the skirt has minimum leakage. The hover train was designed to run on a concrete track, and a development track was built early in the 1970s. In 1973, RTV-31, the first vehicle to test all of the innovations, made its first run. The train travelled at 167 kilometres per hour over the 1 mile, 1.5 kilometre track with great publicity. But meanwhile, development had been progressing on the advanced passenger train for intercity transport. Arguments about cost, speed and efficiency went back and forth, but in the end, the hover train project was cancelled and the APT system was adopted.
Now nearing the final stages of its development, the French aero train will be a considerable boon to intercity commuters when it's brought into service.
The aero train, France's rival to the British hover train, used a similar principle, but like the RTV-31, was mothballed by the government in favour of a fast train that travelled on rails in France, the TGV. Before its cancellation, a number of test trains had been built with different power plants. Several of them were large enough to take passengers. The Aerotrain 02 was powered by a Pratt & Whitney turbojet, the S44, a full-size passenger-carrying car intended for suburban commuter service was equipped with a linear induction motor. And the Aerotrain I-80 was a full-size passenger-carrying car for intercity service. The growth of railways to their present status as mass transit transport systems in every part of the world did not, of course, rely on these exotic experiments. Everywhere, the workhorse for passenger and freight has been the diesel or diesel-electric locomotive. Despite their names, diesel trains are not driven by the power of their diesel engines. They are driven by electricity. The diesel engines power the shaft that drives the generator that powers the large electric or traction motors that turn the wheels.
The diesel engine does not produce mechanical motion directly to create the motion of your locomotive vehicles, but it's used to generate electricity, and then electricity is used to run the AC motor, then you go forward. Diesel engine can be optimized at a fixed engine speed and fixed operating condition. That's how you get the best efficiency.
Typical of the most powerful of the diesels is the AC6000CW, generating 4,500 kilowatts or 6,000 horsepower. The only units that produce more power are dual engine designs. These are the great machines that haul the huge loads. The ore train's massive freight loads. The versatility of the power source means that the power spectrum is wide. The first regularly operating diesel locomotive produced 883 kilowatts of power. The robustness of the diesel and its fuel efficiency compared to the standard internal combustion engine explains its ascendancy in railway, marine, and heavy road applications. But there are drawbacks. The cost and availability of the fuel, the need for regular maintenance, the environmental issues of noise and smell. Where the pros and cons have been weighed, many operators have preferred systems that deliver electricity direct to the train's motors without the need for diesel generation. As with the Shinkansen, this means connecting the train to a live supply, either by an overhead wire or a live rail. The first electric train was demonstrated in Berlin late in the 19th century. It achieved a top speed of 13 kilometres an hour. The technology has advanced since then, and power is now produced in abundance. The power is generated not on board through a diesel engine, but by plugging the railway into the national electricity supply. The Shinkansen, the TGV in France, the Eurostar that links Great Britain to the continent of Europe, are some of the high-speed types of train that derive their power directly from a live source. France's TGV, Très Grande Vitesse, or very high speed, is a typical electric train.
They're fast. The track is built with that train in mind. So the track has to be long radius curves and not rough, but a smooth track. I think the engineering innovation is the design of the whole system to be reliable, to be fast and to be safe at the same time. So that was a rethink of railway technology.
Sleek, streamlined, some even with the duckbill that was first seen on the Shinkansen. The TGV network links every part of France and France with its neighbours. The service was initiated in the early 1970s, and the original concept was for gas turbine power. The oil price crisis of the period put paid to that. Electric traction became the power of choice. And though the look of the locomotives and their performance has progressed since the service was initiated in 1981, the basic principles that get the power to the wheels have not. The TGV's traction components include the pantograph, which maintains contact wire pressure at about 70 N. The main transformer, which converts 25 kilovolts, 50 hertz single-phase overhead power into 1500 volts, 50 hertz, and a number of parts that deliver this power to the traction motors. Thyristor-controlled rectifier bridges, the common block consisting of DC circuit breakers and the main filter capacitor, traction inverters that convert DC into a three-phase, variable frequency AC waveform combined to get usable power to the AC traction motors, which on the TGV are slung from the vehicle body, substantially reducing the mass of the truck, giving it exceptional tracking stability. Each motor can develop 1,100 kilowatts and can spin at a maximum rate of 4,000 RPM. This power arrangement has enabled the TGV to set the world's speed record for conventional trains. Line voltage had been boosted to 31 kilovolts and extra ballast tampered onto the right-of-way when on April 3, 2007, a modified TGV reached 574.8 kilometres per hour. Elsewhere in Europe, another very fast train, the ICE, Intercity Express of German railways, has, like other trains in the category, a distinctive nose shape to deal with the power it has as it pushes through the air.
You know, one of the challenges that we're looking at, in particular with the ICE3, is the slipstream effect of the train. So the ICE3 is just one example of a train where which is travelling at high speeds, and we need to understand how that train is going to induce flow behind it and how that flow is going to impact on surrounding infrastructure, for example. So the shape of the nose, which in the ICE3's case is also the shape of the tail, has a large effect on the flow that's induced. So we see a large downwash occurring, and that's associated with flow over the back of the train. And we can actually see large vortices, which are a little bit like tornadoes, if you like, on a different axis. And those vortices actually move around within the wake, and they can impact on different objects or on people as the platform goes through. So if you're looking directly behind the train, you have a vertical component of velocity, so you have a downflow, and then you have that interacting with flows coming around the side of the train at the rear. And the way that they interact can be such as to introduce vortices. So you have the flow coming down through the middle of the train, and then you have a large rotation, and you get two vortices that a little bit like angled tornadoes originating from the rear surface of the train, and then they can move relative to one another, and they cause a lot of drag. They're associated with low pressure regions, and when you've got low pressure on the back of something, it's acting like suction, so it's pulling it back. And they're not dissimilar in nature to the vortices that you see behind a plane.
Other trains draw their electricity not from overhead wires, but from live rails. Perhaps the most famous of these travels beneath the streets of a city, the London Underground. When trains first started to run through tunnels beneath London, it was 1863, and power came from steam engines. The network, which continues to evolve, now covers more than 400 kilometres and carries almost 1.5 billion passengers a year, serving 270 stations and travelling at an average speed of 33 kilometres per hour. The first electric trains ran in 1890, and since the early 1960s, all London Underground trains have been electric multiple units, self-propelled carriages using electricity as the power source. A contact shoe beneath the rolling stock draws power from the live rail, which is the power source throughout the network. The onboard plant translates the delivered 750 volts of direct current and produces the power that drives the traction motors. The London Underground, known to all Londoners as the Tube, is the oldest underground system in the world. But the Seoul Metropolitan Area system in South Korea holds the record for route length at over 900 kilometres. The New York subway serves the most stations, 468. The busiest is the Tokyo Metro, with 3.3 billion passenger journeys each year. With its Art Nouveau stations, Paris may be the most decorative. And famously, the decor of many stations on the Moscow subway is of extravagant opulence. The technology is in place on many established lines, including the London Tube, for driverless trains. That future is already the norm in the Persian Gulf. The Dubai driverless metro opened in 2009. It covers less than 75 kilometres, serving 49 stations, with further expansion planned. What places it firmly at the forefront of technology is the fact that it is fully automated. Its trains are driverless.
The main thing it's known for is that it doesn't need drivers, and that's an increasing trend with new train systems. It's quite a comprehensive system running the length of Dubai.
Power is drawn, as with far older rapid transit systems, from a live third rail, delivering 750 volts of DC, powering trains on the red line at up to 47 and the green line at up to 38 kilometres per hour.
It's about 75 kilometres of track, and they're increasing that. It started operating in 2009. It's not an unusual type of metro system. A lot of it's elevated. I was there watching it being built for a while. One thing that's a little different to some of the other systems is that its power supply, it's obviously electric, is from a third rail and not from an overhead catenary. The problem with that is that you need to have a secure right-of-way so that people don't get in contact with the electrical circuits. The alternative is overhead catenary that uses a pantograph on top of the train to pick up, and that's certainly the system we see more of in most countries.
The power to move people in rapid urban transit has not always forced trains beneath the ground. Elevated trains may travel on raised rails, like Chicago's L. Maybe monorail designs from Disneyland and Tokyo to the Bangkok SkyTrain. Or they may be hanging trains.
Interestingly, railways don't have to be terrestrial in nature all the time. There are a collection of very interesting suspended railways where the carriages are actually hanging from an overhead rail.
The Wuppertal Schwebebahn. The Wuppertal-Schwebebahn has suspended cars reaching speeds up to 60 kilometres per hour on a line running more than 13 kilometres above the streets of Wuppertal since 1901. The cars are suspended from a single rail built underneath a supporting steel frame with 486 pillars and bridgework sections. Each car hangs on wheels which are driven by multiple electric motors operating at 600 to 750 volts of direct current supplied through the conductor rail. The onboard power supply drives 4 direct current medium voltage motors per articulated train. Special trains have always had a special place in the affections of people. The Wuppertal-Schwebebahn is fondly known as the Old Girl. Trains associated with long, exotic journeys and spectacular luxury have a particular hold on the imagination. The extraordinary, futuristic and very expensive Shikishima is not a train to anywhere. It is exclusively a vehicle for taking short tours in northern Japan. A golden piece of modern design with Michelin menus, all suite accommodation and wonderful observation cars, this vision of tomorrow rides on a rather traditional diesel-electric power plant with a top speed of 100 kilometres per hour.
Japan's very interesting because there are this new breed of luxury trains, the Shikishima, which is ultra-luxury, Michelin chefs on board, beautiful state-of-the-art decoration, comfort, the technology underneath, the running gear, the spring systems under the carriages, ultra smooth, and you never hear clickety-clack anymore and things like that. You've got a welded rail for a start. But the appointments inside these trains is something superb. But it's also the uniqueness, I guess the thrill of running on something that's a bit exclusive, something a bit special. Because luxury trains have always been the preserve of the ultra-rich.
The Indian Palace on Wheels is also a train dedicated to tourism. One of the luxury trains making journeys around the subcontinent, it takes its cue from the decorative traditions of princely India, the distant days of Maharajas and the British Raj. The Orient Express, a legendary name in train travel, is a luxury destination in its own right. In its heyday, linking Paris and Istanbul, the Orient Express was a powerful train that carried powerful people, heads of state, and every sort of celebrity for every sort of success and scandal. And in Agatha Christie's famous story, murder mystery.
Earlier 19th century, in order to realise a market that was there for the wealthy, but also to attract the middle classes to train travel. So the rise of trains like the Orient Express in the 1880s, essentially a very smart business plan to provide comfort and a quality accommodation on a train that you didn't have to change. So it was a matter of doing deals along the way with different governments across different borders to create one train heading across multiple borders.
Equally exotic, but a train with a real and vital communications role in joining the extremes of the world's largest nation, is Russia's Trans-Siberian Railway. The vastness of Russia can be understood by realizing that if Siberia was an independent country, it would be the largest country in the world. The Trans-Siberian, really a network of railway lines that link Moscow to Russia's Far East, is a journey of more than 9,000 kilometers, the longest railway line in the world. Building the line began in the 1890s and was completed in 1916, the year before the Russian Revolution.
Russia, interestingly, has a unique developmental railway story where the Tsar decided that he would have a different gauge when it came to the construction of railways on a large scale in that country, and randomly came up with 5 foot. as a broad gauge, unique to his system. The Tsar broad gauge, it's referred to. And that, even though it caused all sorts of problems when it comes to transshipping at the borders with Poland and with China, ultimately, when the Trans-Siberian Railway got that far, it did create all sorts of bottlenecks when it came to the First World War and the Second World War. So it did do its job in helping to protect borders.
The Trans-Siberian is no tourist novelty. It continues to be the most important railway line in Russia. 30% of the country's exports travel on the line, and its connection to the Trans-Mongolian makes it an important outlet for Chinese exports to Europe. About 200,000 freight containers a year reach Europe on the Trans-Siberian. The fastest train on the route, which was fully electrified in 2002, takes just over 6 days to link Moscow to the Pacific Ocean. An average speed of 64 kilometers per hour across 5 time zones. After the Russo-Japanese War of 1905, in which inadequate railways meant the failure to reinforce the Far East, the Trans-Siberian received heavy investment, which paid off in the Second World War, when moving the Siberian Reserve to meet the German invasion was crucial to the Soviet Union's survival.
Here are 3 of many good reasons why there'll be a warm reception for the Nazis if they try an invasion.
Almost since the first train pulled the first wagon, trains have been part of military planning and military weapons.
It was the 1850s that also saw the first use of trains extensively in war, something that was to become a major theme for the next 100 years. Troops were brought to the front en masse by train in the Crimea War, helping to create one of those interesting things that we saw a lot of in the late 19th century and certainly through the 20th century, the stalemate of war, trench warfare, and the use of heavy artillery that could be brought to the front pretty quickly by train, creating massive war front and huge loss of life, of course. The American Civil War, effective use of trains.
During the American Civil War, volunteers from the Union Army commandeered a train and took it north. As they went, doing as much damage as possible to the vital rail line from Atlanta to Chattanooga. They were pursued by the Confederate forces at first on foot and later on a succession of locomotives. The event was reproduced in one of the great achievements of silent cinema, Buster Keaton's 1926 film, named for the featured locomotive, the General. Since that event in 1862, trains have often played a role in the massing of armies, their supply and support, and the carriage of heavy weapons. In the Second World War, with industry in America from coast to coast gearing up to be, in President Roosevelt's words, the arsenal of democracy, it was the railways that were vital to moving war materials and personnel to the ports, and so to the battlefields.
Then, railways allowed troops to be delivered to the front, like a sausage factory, continually.
And it was railways that made possible the carriage and the use of the largest caliber rifled gun ever used in combat, Chewewa Gustav, Heavy Gustav. Originally designed to take on the fortified French Maginot Line.
You had some very interesting technologies developed specifically using railways. The massive rail-mounted armoured guns and cannons, which are as big as anything on a battleship, if not bigger, where they would fire 14-inch, 16-inch shells, I believe, as far as miles into the battle zone from track-mounted guns, recoiling great distances down the line as they fired these extraordinary salvos, much bigger than anything could be managed on conventional land arrangements.
Also produced by Krupp's was the slightly smaller but far more practical K5, which could fire a 255 kilogram shell 64 kilometers at the rate of 15 rounds an hour. "25 of the guns were produced and they were used in France and in Italy. The limitation in sighting the gun was that its effective aim could only be achieved vertically, limiting the gun to targets in line. To track targets on a horizontal axis, either a curved length of railway was used with the gun shunted backwards or forwards to aim, or for 360-degree traverse, a turntable could be constructed, consisting of a raised rail section, the firing bed, which carried the gun, running on a circular track. It was the K5 that formed the basis for the M65 atomic cannon. Developed in the USA after the war and nicknamed Atomic Annie. Although based on a railroad gun, Atomic Annie was towed by special tractors and was capable of firing a nuclear shell.
So the M65, the Atomic Annie, or the atomic cannon, was very much a product of its time. This weapon was designed to be used by land forces to fire a small nuclear round, bomb, at enemy land forces and create what you'd call the nuclear battlefield. This is quite an enormous weapon. Its caliber is, I believe it was 280 millimeters, which is the equivalent of an 11-inch gun. And its origins would have been from some of those very heavy artillery pieces that existed in the First World War and in the Second World War. And weapons of that size were originally mounted on railway carriages because that was the only thing that was strong enough to pull them around.
In military use, trains have not only been valued as a means of transporting weapons and manpower, they have been used for speed.
One of the uses of a high-speed rail track is to test the flight characteristics of a guided missile submunition. So in the very early developmental stages, they'll run a new missile down the test track. At the end of its travel, they can stop the sled dead, which will release the missile going forwards, and then allow it to impact with a target, and that way you can simulate in a very closed environment the impact of the missile with a target array.
The 846th Test Squadron of the US Air Force broke the world speed record for a vehicle travelling by magnetic levitation on a test track in Otero County, New Mexico, when a rocket-powered maglev sled reached a top speed of almost 1,020 kilometers per hour. The Air Force used superconducting magnets to move the sled without it touching the ground. The maglev system is the most recent rocket sled, and its speed record surpasses that of the sled that powered by 9 solid fuel rockets with 40,000 pounds of total thrust for 5 seconds that accelerated Colonel John Stapp of the US Air Force to a speed of 1,017 kilometers per hour at an Air Force base in New Mexico on December 10, 1954. Stapp, who was known as the fastest man on Earth, was not concerned with how fast a man could go, but what would happen to a man subjected to major G-forces on rapid acceleration. And he demonstrated that a human being can withstand 46 G.
Colonel Stapp, the fastest man on Earth.
From the start, the appeal of railways has been their ability to move large loads over long distances. Power has been decisive in determining how large the load, how far the distance. In one great and barren part of the world, where distances are vast and loads enormous, the train is king.
The task for a heavy haul railway is the same the world over.
you want the cheapest method of getting from mine to port. One way of doing that is to have the optimum number of locomotives and the optimum number of wagons with as much as you could possibly fit in, which comes down to how well your track is constructed for how much you can actually put per train.
In Western Australia, there are mountain ranges made of iron ore. The job of getting the ore from the mines to the ports is work for the longest and heaviest trains anywhere.
A long iron ore train, fully loaded, will take several kilometres to stop. It will stop quicker if it's on an uphill grade, and it will take longer if it's on a downhill grade. These are the simple Newtonian laws, and they apply to iron ore trains as well as everything else. So you need a really good braking system, and you need very powerful locomotives to get you up the grades. And it isn't a solely downhill run from mine to port. There are some uphill grades as well.
In the Pilbara region, ore trains typically approach 240 cars, or around 30,000 tonnes. The standard for Rio Tinto operations is 29,500 tonnes of iron ore, carried in a train 2.4 kilometres long, hauled by 3 locomotives. A BHP Billiton ore train has typically 268 cars and a train weight of 43,000 tonnes, carrying 24,200 tonnes of iron ore.
The skill in driving a fully loaded iron ore train is considerable, because if you accelerate or decelerate incorrectly, you could break the train. So if you're imagining you're going over a hump, you have to be careful that you don't put so much tension between the couplings of the wagons that could actually cause the train to break in two. So it's very difficult to drive such a train.
The record was set on the 21st of June 2001, when a train comprising 682 wagons with a total length of 7.352 kilometres, hauled by 8 6,000 horsepower General Electric AC 6000 CW diesel electric locomotives and controlled by a single driver, travelled the 275 line to Port Hedland in Western Australia. Each AC 6000 CW 6,000 horsepower, 4,500 kilowatt loco was powered by a V16 twin turbocharged engine. There is a spectrum in train travel, and here is the opposite end of it from the ore-carrying behemoths. This is Miniature Wonderland in Hamburg, Germany, the world's largest display of model railways. Construction began in 2000 and is set to continue into the future. The present scale of the operation is remarkable. More than 7,000 square metres of floor space house an exhibit that boasts almost 15,500 metres of track, along which more than 1,000 trains run through 1,300 signals. In a world populated by about 265,000 figures. The exhibit suffers the theft of about 3,500 every year. So far, building Miniature Wonderland has cost about 20 million euros and employs some 270 people. Included in the landscape is the world's largest model airport, an advanced automated system to move cars around the layout, and a control system operating through 50 computers. There is something fantastic about the world of the Miniature Wonderland. But there are even more fantastic, futuristic plans on the drawing board for train travel into the future. And the most futuristic thing about many of the designs is the power source that they will use. The Hyperloop concept, in an advanced stage for Dubai and proposed as a high-speed link between cities such as New York and Washington, promises to revolutionise not just the speed, but the way in which we travel by train. The Hyperloop concept operates by sending specially designed capsules or pods through a steel tube maintained in a partial vacuum.
One approach to ground transport in the future that's being considered is if you can have trains effectively or capsules operate in a vacuum, then you've removed the aerodynamic problem. Now, this is a really long way off, but if it was to work, that aerodynamics wouldn't be a problem, so you could achieve extremely high speeds.
The first thing to imagine afresh is the railway station. Pods constantly shuttle into and out of terminals, and passengers step on and on arrival step off the moving car. Each car with perhaps a capacity of 6 to 8 passengers. The original concept for the look came from Elon Musk, whose design envisages each capsule floating on a 0.5 to 1.3 millimetre layer of air provided under pressure. This thin layer provides a more achievable and more practical tubular concept than the original vacuum tube from which it has evolved. The vacuum tube, offering zero air resistance, could accommodate theoretical speeds of thousands of kilometres an hour. The thin layer buoys the pods while still allowing for speeds that wheels cannot sustain. Linear induction motors located along the tube accelerate and decelerate each capsule, with rolling resistance eliminated and air resistance greatly reduced. The capsules effectively glide for the bulk of the journey.
You remove the air, so you're removing the aerodynamic force, and so it's like travelling in space. Effectively, that's what you're trying to do. Create a little tunnel, space tunnel, but you don't have aerodynamic drag. Which is why you can travel so fast in space without having so many problems, because if you were to travel at those sort of speeds that space shuttles travel at through the atmosphere, you would generate enormous amounts of heat.
The original Hyperloop concept placed an inlet fan at the nose of the capsule to transfer high-pressure air building at the front of the vehicle. Pods are projected to reach a top speed of 1,220 kilometres an hour, meaning that the journey from New York to Washington would be accomplished in just under half an hour. The story of power on the rails started with the search for a smooth journey and reduced friction. It continued with streamlining and improved ways of producing power, and with the Hyperloop, it reaches the points of almost eliminating friction, getting rid of rails and generating enormous speed, but requiring the expenditure of very little power. Podcars, PRTs, or personal rapid transport systems and hover trains are on drawing boards and in some cases exist and are being tested in various parts of the world. In some places, typically airports like London's Heathrow, PRTs are already an important part of the transport infrastructure, as podcars shuttle passengers between terminals, from terminals to public transport of car parking hubs. Designs that not long ago belonged in the realms of science fiction are now carrying paying passengers, and the power of the railway, transformed though it might be, shows no signs of diminishing.